So today is about almost exclusively about ways of exploiting the fact that modern HPC systems are actually shared memory clusters of shared memory nodes. I mean, that's been true for 15 or so, more than maybe 20, even 20 years. And there are two ways of exploiting that. One is to combine the message passing distributed memory and threaded shared memory models, MPI and OpenMP. And the second way is to use new functionality, well, relatively new functionality in MPI to do that. So I'll spend the morning on MPI plus OpenMP, and then talk a bit about the RMA access model in the afternoon. All the exercises are based on a very simple traffic model. So I will give it's a very, very simple, extremely simple model. It's really just an exemplar of a very simple code that does local stencil-based updates, nearest neighbor updates, and a boundary swap through halo swapping. It's really just a test bed to try these things out. I'll maybe give if you've not done the introductory course, the EPCC introductory course, you may not be aware of it. I'll maybe spend 5 minutes just explaining that. So I suspect that the first session will be about 3/4 an hour lecture, then about 10 minutes talking about the traffic model, then about half an hour practical, taking us up to coffee. But I will get started now and here. Sorry, where are we? PowerPoint. Okay, so you should have these slides there. So what we're going to talk about is MPI and OpenMP. I'm going to get my windows in order. So I will give a motivation. So there's one slide deck here. Don't be scared. There's a lot of slides here. But what I will do is I'll give a motivation, talk about potential advantages and problems, and then we will then I'll just have a session where you familiarize yourself with both MPI and OpenMP versions of this traffic model. And then after coffee, excuse me for talking with my mouth open. Oh, didn't mean to do that. Sorry. After coffee, I will talk about the actual styles of MPI plus OpenMP, and then my cursor. Oh no, it is there. And then we'll talk about the MPI thread interface. So I'll stop sort of roughly halfway through the slide deck, and then carry on after the coffee break. So what's the motivation? Well, it's very hard to buy a single CPU. In the early days, well, late 90s, for example, if you were building a distributed memory system in the style of ARCHER2, which maybe the early Cray systems, T3D, T3E, which we had in Edinburgh, you bought lots of single core CPUs and networked them together. So the early machines had 256, 512 nodes, but each node was a single core, single CPU core. And then, there was also a style of parallel computer called a shared memory computer that had multiple CPU cores, but they had to have special hardware. So people like Silicon Graphics in those days, and Sun, and everybody had their own hardware to string multiple CPUs together, attached to the same memory. But that was all so there was very, very much two different types of computer, distributed memory and shared memory. However, nowadays, a single chip, CPU has multiple cores on it, so you cannot get a single core processor anymore. So what we have are these clustered architectures, where each node is a shared memory multiprocess, and that used to be 248, and now it's up to the hundreds. On ARCHER2 we have 128. ARCHER2 has 6,000 nodes, 6,000 computers, each with 128 CPU cores on them. And the important point is within a node, within a computer, you have a single address space. That means that in principle, there's a single block. You have a single block of shared memory, and I always think of it as a shared whiteboard in an office. Any processor, any person in the office can in principle read and write to the same location on the whiteboard. Now, the reason you can't do that in MPI is that the way the operating systems are set up is when you create a process, and MPI is built from operating system processes, they're ring-fenced from each other. So memory is quite complicated now. You have virtual memory and such like, but so processes are ring-fenced from each other. But at a hardware level, an ARCHER2 node has 256 gigabytes of memory, and in principle, any CPU core can access any part of it. The reason they can't in MPI is because the way the processes work, the memory is kind of ring-fenced from each other. But so you have a single address space with each node. So in principle, you read and write directly to any memory location on your 256 gigabytes. But separate nodes have separate address spaces. They're separate computers, basically. And so how should we program such a machine? Well, the normal way in MPI is you just ignore the fact that the processes are sometimes running on the same node. You use MPI across the whole system. As a programmer, you think of ARCHER2. If you run a 32 node job on ARCHER2, you think of it as being, I can't do the math, is it 32 times 256, 8,000 or whatever individual processes. And the fact that they're arranged as groups of 128 processes sharing the same memory space, you could pick up from the performance that those processes might be faster talking to each other. But functionally, the way you program your application, you just ignore that. We cannot in general use OpenMP threads across the whole system. That's because basically the threads need to be, all threads need to be within the same address space, the same memory space. Threads need to be running on the same computer to communicate, to work. What I mean by computer, I mean threads are small, but they need to be running on under the same operating system. So your operating system manages your threads. So you have a single, hold on my laptop, you have a single node of ARCHER2, which is just like a multi-core laptop with an operating system, and the operating system can manage the threads and move them around within that node, but it can't offload them to another node. Some people have come up with software solutions for this, but it's very expensive, inefficient. It's also possible in hardware, but also it's very expensive. So nowadays, I think you should think of threaded programming, OpenMP allowing you to do parallelism within a node, within a computer, but to do internode stuff, you need to use MPI. But it was a very obvious question very early on. Could we use OpenMP threads within a node and MPI between nodes? Well, it's kind of obvious that you can, because all the MPI says is I have communicating processes, and those processes can create threads if they want. I mean, there's nothing stopping them. But is there any advantage to this, I think? And so people started doing this quite early on, and there was some support. There are some subtleties with it. MPI needed to be extended slightly to support this model, although people experimented with it before it's officially supported. But really, is there any advantage to this? I think is the main question. In general, MPI plus OpenMP does not improve performance for small when the MP application is scaling well. And that's why it's rather difficult to give you exercises, because it's unlikely that any exercise I give you will show improved performance for MPI plus OpenMP, because it'll be too small and running on However, the exercise, the traffic model, is there to illustrate how you can write hybrid MPI OpenMP applications. However, the benefit comes when MPI scalability starts to run out, and the scalability can be in two regimes. One is time. In other words, you increase the number of MPI processes and your code stops going any faster, then you might be able to extend that scalability through using OpenMP. Also, in terms of memory, we'll see that you may actually say, well, I'd like to run 128 CPU core. I'd like to run 128 MPI processes on each ARCHER2 node, but it runs out of memory. And so you might be able to scale that up. Well, I can actually use all 128 CPU cores by running 64 MPI processes, having each of them doing 2 OpenMP threads. So MPI plus OpenMP may extend scalability as larger core counts. But the reason that I think the first part of this talk is always putting you off doing it, the reason is that we'll come back to this, but introducing OpenMP to an MPI code for a little test code like we're going to do today is pretty straightforward. But introducing OpenMP into a very, very large, tens of thousands of line HPC application is potentially a lot of work. And so you really need to have a reason before you start doing it. You think it's going to go faster. Don't just embark on it. Spend 6 months adding OpenMP to your program and come back and say in 6 months, oh, it didn't go any faster. What if that was obvious from the outset? And so this is the kind of typical performance curve for pure MPI. For small numbers of cores, you might expect to get better performance, but then it runs out. MPI plus OpenMP might start off a bit slower, but could extend out to a larger scalability, and that is the kind of that's what people do. So what are the potential advantages of MPI plus OpenMP? Well, there's reduced memory usage, which we'll talk about, exploiting additional levels of parallelism, which we'll talk about, reducing load imbalance, and reducing communication costs. I'll touch on those slightly here. So reducing memory usage is an interesting one. So actually, I was chatting to somebody yesterday after the lecture, and some MPI codes use a replicated data strategy where all processes have a copy of the major data structure. And the person I was speaking to yesterday said that because they were using dynamic, they had a mesh, they had a domain which was being dynamically refined. The mesh, their problem mesh, their grid was evolving with time. And because of that, the only practical way to allow that to happen was to have where every process had a copy of the entire mesh, the entire grid. Now, if that seems wasteful on ARCHER2 because you have 128 MPI processes on a node, and if that mesh is a gigabyte, then in MPI every process has to have its own copy. So you have 128 gigabytes, which is 128 replicas of the same thing. Wouldn't it be nice to have if you'd written that program in OpenMP, you'd have just stuck that mesh, your grid structure, into a shared array and had one copy per node, which is 1 gigabyte. So this used to be a bit of a corner case a few years ago when you had 2 or 4 CPU cores on a multi-core processor, but now we have hundreds. It's a really big deal. You might say, I don't have any replicated data in my program, but actually, when you do domain decomposition, even just domain decomposition with a halo, that halo is replicated data. What you've done is you've taken a copy of the data that exists on another process. Now, it's a surface to volume effect, but it can be surprisingly large, and we'll have an example later on. MPI itself, every process is running the entire MPI library, and so it'll have its own software stack, its own buffering and internal data structures. So, MPI, the internal buffers may use up a lot, consume significant amounts of memory, and that can be especially true if you're doing very big collective operations. So, for example, a lot of codes that do Fourier transforms end up transposing large data structures. You can think of it going from a row-wise decomposition to a column-wise one. That is often done through calling an all-to-all, and the MPI library is having to manage and buffer huge amounts of data when it does that, and that can be a significant overhead. A pure MPI code needs 1 copy per process or core. I would say that one of the things which is clear since multi-core processors became into existence, there are a couple of terminologies which are ambiguous. Processor is a slightly ambiguous term, and CPU is an ambiguous term, unfortunately. To me, a processor is a core. So I would think of ARCHER2 having 128 processors per node, but to a hardware person, a processor is the thing you buy in the store and stick in. So anyway, you need to be careful. But a pure MPI needs 1 copy per processor core. A mixed code running, of these message of all these data structures, a pure MPI code needs 1 copy per processor core, and a mixed code only require 1 copy per node. So that could potentially be a very good, a big saving. And this is becoming increasingly important. The amount of memory per core is not likely to increase in future. Again, this came up in our conversation yesterday, that memory is expensive, power hungry, whereas as I'm not a hardware guy, but as production processes get better, it is, I think, remarkably simple to say, well, I used to give you 32 CPU cores on a die. Now I'll give you 64. I mean, and that's stamped out. It's relatively straightforward and cheap. So it's quite easy to increase the number of CPU cores. The amount of memory doesn't increase for a bunch of reasons, and therefore the amount of memory per CPU core is dropping typically. So we talked about the Halo system. Now these slides actually developed by a colleague of mine, Mark Bull, who's much more of an expert on OpenMP than me, so I'm not taking credit for these slides. If you're scaling up to very large process counts, using more process implies a smaller domain size per processor, unless you can genuinely weak scale. And most, there's different modes of parallel computing, but most people are looking for strong scaling. That is, I want to solve the same problem in a shorter wall clock time, which means you have smaller problem per node. So the amount of Halo data does decrease as the local domain size decreases. It amounts a significant fraction of the storage. So, for example, if we have a 50 cube local domain, and we say, well, we're going to do boundary swapping, so it's actually not going to be 50 by 50 by 50, it's going to be 52 by 52 by 52. The Halos take up this amount of data, which is 11% of the volume. But then if you then maybe run on, I can't work out how many more processes, there's maybe 10 times as many processes, you're up to a local data size of 8,000, and that is, then you have the Halos start to take up 25%. And if you're on a 10 cube local domain, then you're using almost 50, coming up to 50% of your data is in Halos. And so that's showing that your actual total memory usage goes up significantly as you increase the number of processors. And then it becomes much worse if you have more than 3 dimensions, as some codes do. But also if you have deep halos. Now, so what I mean by deep halos here is that I've assumed here this is a nearest neighbor interaction. That means that a particular grid point ij only needs to interact with I plus 1, I minus 1, j plus 1, j minus 1. However, if you have a next nearest neighbor scheme, then your halos would have to be twice as deep. And so this wouldn't be 12. This would be 12 cubed minus 10. It would be 14 cubed minus 12, 10 cubed. And I can't work out 14 cubed is. What is 14 cubed is? But 14 cubed is 2,500. So if you here, it would already be much more data in these halos than in the actual in your main arrays. So that's the first thing at reducing memory usage, either through explicitly replicated data structures becoming shared, or through this sort of slightly more additional effect of halo data, boundary data. Some MPI codes don't scale well beyond a certain core count because they run out of available parallelism at the top level. And so, for example, I could imagine you had a that's kind of a fake example, but imagine you were doing simulations of the fuel efficiency, the heating efficiency of houses. Okay, so you've got a simulation that runs within a house. Well, simulating the way that heat flows and whatever in a house is very, very complicated. And so you might want to do that with OpenMP, which has lots of things to do with dynamic tasking, load balancing, all kinds of stuff. So the simulation of a single house might be easily done in OpenMP. However, if you have multiple houses, then you might say, well, that's easy. I can do that with MPI. I can give a different house to a different processor. The problem there is if you want to simulate a town of 1,000 houses, you can't go beyond 1,000 MPI processes, because you need to have a single MPI process. In pure MPI, what you're saying is the simulation, there's certain parts of the simulation, which is the complicated stuff within this very complicated house, which are too difficult to do with MPI, so I'll do them with OpenMP. And so you run out of parallelism at a certain point. So you might be able to have additional lower levels of parallelism, but in principle, this could also be, although in principle it could be done with MPI, in practice it might be hard. As I said, there might be load balance problems, irregular communication patterns, all of which are very hard in MPI, but simple in OpenMP. And often these may not be in principle things, they may be practical things. They may be design decisions in the original MPI version, which mean that you can't go any further. So there's a, sorry, I'm just jumping ahead. So I meant to put this in here, so apologies. And one of the design decisions is, which I'm not drawing down. Now I should, sorry, apologies. I thought I had put this, I thought I put this slide in, but I will try and do it with, I should have done this with a slide on. This is, it's just because it's, so what you often have is you might have, you have a cube of data that you want to, sorry about, apologies that this diagram wasn't already done. That's my oversight. I'm doing this very badly, but there's a cube of data. And you're going to want to, at some point in the program, your parallel program, you're going to want to do Fourier transforms. Well, it turns out it's much easier to do that if you split the data into slabs, slab decomposition. So here I'd split into 4 slabs. That's because when you're doing Fourier transforms in the X or the Y direction, they're completely local to the process. And it's only in the Z direction you have to do a data transposition to get it like that. Now, you may have made that design decision right at the start when you wrote your MPI program. You might say, right, this is the way I'm going to write my MPI program, okay? The problem there is, if you have a 512 by 512 by 512 problem, you cannot run it on more than 512 processes. You run out of parallelism. Yeah. Now, the correct way to fix this is to do maybe something called a slab-based parallelism. You introduce another dimension of parallelism, and you divide your data into pencils, which people call it, which would be to do something like this. However, that may be very hard to retrofit. And so you may be stuck with this design decision where you have a slab-based decomposition, meaning that you cannot, if you run on an L-cubed problem, you cannot run on more than L processes. So that on ARCHER2, if you're running, say this was 128 by 128 by 128, you couldn't, sorry, 512 by 512 by 512, you couldn't run on more than 4 nodes of ARCHER2 because that's 4 nodes of ARCHER2 is 512 processes. However, what you could do is say, well, I'll give each slab to an MPI process, but I'll parallelize within a slab using OpenMP. And that means that in principle, your scalability goes from 512 processes to 512 nodes, which on ARCHER2 is a factor of 128. So as I said, these, apologies that that wasn't there as a proper diagram, my oversight. You know, there may be in principle issues why you can't exploit all your parallelism in MPI, or there might be practical ones. And if you've ever the early decisions like this, like the domain decomposition, if your code is decomposed of 1 or 2 dimensions, can often be baked in very heavily to your code and very difficult to undo. So for practical reasons, it may be easy to exploit the additional levels of parallelism using OpenMP, because OpenMP has a lot of support. It's incremental. There's lots of support for load balancing and such like. I mean, it may not be performance optimal, but it may be the only practical way of doing it. We've said here that obviously OpenMP can't extend beyond a single node, but because actually the number of cores per node is going up, this is actually the benefits of OpenMP parallelism are potentially increasing with time. You may have written a hybrid MPI OpenMP code 10 years ago and said, well, I have 8 CPU cores per node, doesn't help me, but now with 128 it might. So the next thing you might want to do is to reduce load imbalance. Load imbalance is a very difficult problem to solve in MPI, because although you might identify that one MPI processor has too much work to do and you'd like another MPI process to take some of it, transferring the work also involves transferring the data. And so you have to try, and that might mean that transferring these small tasks may not be beneficial. Often doing this load balancing requires a completely global view of all the data, which is very difficult to do. Often people maybe only restrict to transferring loads between neighbors. You have a load balancing model which is diffusive. You say, if I have more work than my neighbor, I give it to my neighbor, and then slowly the load will hopefully. But it's very, very difficult to cope with load imbalance in message passing problems. However, as I mentioned yesterday, OpenMP load balancing between threads is much easier. You need to transfer the tasks, not the data. You can just say, well, this iteration I did that thing, but next iteration could another thread do it, please. And not only that, there is inbuilt support in MPI through tasking and the dynamic schedule for doing this by hand. So it's a massively challenging programming task in MPI. In OpenMP, it's baked into the compiler. So with application of load balance problems, keeping the number of MPI processors small can be an advantage. It might be quite easy to load balance across 4 nodes, but not across 512 processors. And the final thing is reducing communication costs. I mean, it's obvious. Your first idea is that communicating between 2 threads on a node is much quicker than communicating between processes. It's the direct read and write and no library calls. However, actually, this may not be true for 2 reasons. One is memory speeds are very, very slow these days compared to clock speeds, so software overheads are actually quite small. And secondly, we saw that MPI has lots of tricks, that if you send a message between 2 processes on the same node, it's heavily optimized. And in fact, this is really the bottleneck in MPI. People, it's like if you have a hi-fi. The sound quality is dominated by the poorest part of your hi-fi. There's no point buying gold-plated speakers if you have a really crummy, well, in the old days, a crummy turntable or crummy amp. So basically, although you might be able to increase the speed of communication within a node by using MPI plus OpenMP, that isn't actually the limiting factor. Your program will probably be limited by the communication from the network. However, often MPI could communicate more data than is actually required. And this is an example on the next slide, which is just an example from the not quite yet, from ECMWF. In the early days of MPI, when MPI implementations weren't very optimized for distributed, for shared memory systems, it could actually have been, it was actually sometimes beneficial to do a collective operation like an all reduce by doing the all reduce locally on a node with OpenMP, the reduction on a node with OpenMP using OpenMP reduction variables, and then do the global reduction across nodes using MPI. Now, I mean, you can come across examples where you can get some benefit, but what's actually happened is that the MPI developers have got wise, and basically MPI now probably takes care of this itself. The collectors are probably heavily optimized. So we used to have examples which showed that you could beat pure MPI by doing in collectors by using MPI plus OpenMP, but I've not seen one of those for a while. So this is more of a bit of a historical example. The example which was used, which was very successful, was the European Centre for Medium Range Weather Forecasting has something called the Integrated Forecast System, I think, IFS weather model, and they have it's quite obvious to notice that to say that if the wind is blowing in a certain direction, you only need to communicate data in that direction. Okay, so if the wind is blowing in this direction, okay, I need to know. So the wind is blowing in that direction. I need to know what's going on down here, but I don't need to know what's going on up there because the wind's going the opposite direction. However, in MPI, it's very difficult to do to accommodate for that. With that, it's very difficult to say, oh well, actually, I don't need to send data to you because the wind's blowing the opposite direction. Because one of the main reasons is you might say, because the MPI is two-sided, send and receive. If this guy isn't sending to that guy, this guy needs to know not to initiate or receive. So you need to tell this guy, I'm not going to send data to you, and then you might as well have just sent the data in some sense. So basically, the MPI solution is to communicate all the data that you need. Well, that means very, very deep halos. You say, I will communicate a large slab of boundary data to allow for the fact that the wind could be blowing in any direction, and no matter what direction it's blowing in, I'll have all the data that I need in whatever the wind speed times the time step is. And that turned out to be very, very costly because it ended up with very, very deep halos and lots of extra data. What they did is they did an MPI plus OpenMP solution. So within a node, they only did this transfer between nodes. Within a node, with an OpenMP, you could just read the data you need rather than having to communicate it. So basically, the example is that you have the wind is blowing in this direction, so you only need to communicate this data to these processes, not that one to there. In MPI, you'd have to communicate all that data. In OpenMP, if these are now threads, they can just read the data they need without having to explicitly transfer it. So so one of the things that MPI is very difficult to cope with is dynamic communications patterns. It's very difficult to say, oh, on this suddenly, oh, I don't have any data to send to you, so I won't send you anything, because unless the recipient knows that, they will issue to receive, they'll receive no data, and they will then have a deadlock. So this is a particular example. So this was an example where I think the fundamental reason that the communications pattern was data dependent, the communication pattern was dynamic, which is easy to cope with in OpenMP, but not easy to cope with in MPI. So I'll just outline the problems before we start to talk about the traffic model. There's a number of different problems: development, maintenance costs, portability, libraries, and performance pitfalls. So basically, you've got two programming models going on at once. So development and maintenance in terms of the software level will be harder than for a pure MPI code. So OpenMP is easier than MPI in general, but it's still parallel programming, and you need another skill. And also OpenMP is much more subject to subtle race conditions and non-deterministic bugs. So for example, if you make a mistake in an MPI program, it typically does one of two things. One of three things. It gives spectacularly wrong results, it deadlocks, or it crashes spectacularly. It's quite rare in MPI, it's not unheard of, it's quite rare to have bugs where your code sometimes runs and other times runs and gives a reasonable but wrong answer. In OpenMP, you get these race conditions where two threads are updating the same data element at the same time. It's very easy to have non-deterministic runtime bugs. So correctness testing can be hard. I should say that the model always here is that in practice, you're starting off with an MPI code and adding OpenMP. So what you're saying is you have a high level parallelism in MPI, then you're doing OpenMP. It's in practice, almost nobody would ever do it the other way around, have an OpenMP code and introduce MPI. But in the back of my mind, the assumption is you have an MPI code, it's not scaling as you want it for either memory or time reasons. You want to improve it with OpenMP. Portability, MPI and OpenMP are both highly portable, not perfectly so, but combined MPI and OpenMP is less portable. We'll see that thread safety, we'll see there are various levels of difficulty or models of programming in this hybrid mode, and if one of them requires your MPI to be thread safe, and not all, now actually this is less true now, but at least it's not 100% guaranteed that all your MPI libraries will be thread safe. We'll come back to this. Also, you really want to be able to run a standalone MPI code. You want to be able to say, look, introducing OpenMP has overheads. If there's no benefit from MPI plus OpenMP, I want to run a pure MPI code, not an MPI plus OpenMP code with one OpenMP thread. That could be a challenge. To make it compile as a standalone OpenMP code is, in practice, very challenging. So there's a whole bunch of software development issues here. which can be difficult to, that makes it quite difficult to maintain. Libraries are another issue. You may have a program which, for example, so remember the fundamental thing here is that if we're running a hybrid MPI+OpenMP program, we will run fewer MPI processes than we have CPU cores. So, for example, on ARCHER2, on 128 CPU core node, we might run 32 MPI processes, each which has 4 OpenMP threads, giving our 432s a 128. If all your code is explicit, you've written all yourself, you can then go into all your sections of code and put in OpenMP loops to use all that additional parallelism. The problem is, if you call a library like a Fourier transform library, you will now only be calling it, in that example, with 32 processes per node. So if the pure MPI code uses a sequential library, then this becomes difficult. So you either, yeah, it's difficult. The other problem is you might say it's okay, my library uses threads, it's threaded, I can tell it to use threads, but if it doesn't do the threading with OpenMP, then you can get lots of problems that you get twice as many threads as you. It's very, very so this is one of the problems that you face with a hybrid MPI+OpenMP Pro. You have to check that all your libraries that you call, often things like FFTs, are capable of running in that mode. And also performance pitfalls. You're adding OpenMP can introduce additional overheads. There's a whole bunch of issues in OpenMP, synchronization, false sharing, and such like. The other big problem is you've added a tunable parameter. So if I imagine you've got an application and it's pure MPI, and then you give it to somebody and say, could you introduce OpenMP? And they come back 6 months later and say, yeah, I've put OpenMP into your code. Well, previously you had one choice, which was 128 MPI processes per node. Now you have 128 MPI processes and one OpenMP thread, 64.2, 32.4, 16.8, 8.16, 4, 32, 264, 128. You could go from 120 MPI processes and one OpenMP thread to one MPI process with 128 OpenMP threads. You have a tunable parameter, and that means you have to do a scan to find out what the optimal is. And the final thing is the placement of the MPI processes and OpenMP threads can have performance consequences, and we'll have a little exercise, one of the exercises to look at that. So, so basically, sorry, I'm just trying to think. Yeah, sorry, I know where I am. Sorry, I'm slightly behind where I expected to be. But so the other problem is that what happens with when you run, imagine we have a system with 6 processors, 6 CPU cores, for example. On ARCHER2, there's 126. When you run MPI, you're running a single MPI process on each CPU core. So each CPU core is active all the time, doing something useful, doing computation. If you do MPI plus OpenMP, as I've said, you're maybe at an extreme level, you might launch one MPI process here, and you can only use up all the CPU cores when you enter OpenMP parallel regions where you spawn an additional 5 OpenMP threads. That means that any piece of code you haven't added OpenMP into is running sequentially. And so it's like AMDAS inside a node. You have to parallelize everything, otherwise you get very poor performance. And again, for test programs with 2 or 3 subroutines, that could be easy. In a real application program with hundreds of subroutines, that could be very, very tedious and time consuming. And there's a whole bunch of other things which are a bit more advanced than that I won't yeah, I mean, there's a whole bunch of technical things which I won't go into here, but basically this is the major problem that I see, that unless you parallelize with OpenMP every function call, every subroutine, every computationally expensive loop, then you end up losing a lot of performance. The final thing is these NUMA effects. Modern I can maybe, actually illustrate this on ARCHER2 with a there's a nice diagram on our website. Okay. So I'll share a different window. Hopefully you can see that. Yeah. So OpenMP, the model is on ARCHER2 you have 128 CPU cores, all access to 256 gigabytes of memory. That is logically what you have, but under the hood it's more complicated than that. There are actually two processors, two 64-core processors stuck together and connected up. So we call these sockets because that's what you stuck in, connected up by some transport. So logically you see 256 gigabytes of memory, but in fact what it is at the hardware level is two processors each with 128 gigabytes. And so that means that if this if threads here access their memory, it's fast, but if they access memory on a different processor, it's slower. And actually, it's actually even more complicated than that on ARCHER2, because even within a core, even within a CPU, you have 4 blocks of memory connected, each with even a finer subdivision. On the memory level, ARCHER2 actually has 8 different blocks of memory. So in fact, there are the memory access speeds can be wildly different between these processors accessing their own memory, or this guy's memory, or a memory on a different socket. And that's because all modern systems are at some level non-uniform memory access, which is just a hardware feature because we cannot build very, very large Dave's got, if you understand actually the process spread across sockets, that depends. And there's an exercise. One of the first exercises is to check. They can be, yes, but you have to be careful. And that's one of the other thing you have to do. And that's one of the exercises. That's a very good question. But I have an exercise to illustrate that. Is that okay? There's basically the way that Linux allocates memory is very dumb. It allocates memory to the first person that accesses it, and that turns out in OpenMP you can end up with memory being accessed on the wrong NUMA region. So basically, what I'm trying to say here is that it's quite hard to get OpenMP programs to scale beyond the NUMA region, beyond the single non-uniform memory access region, because outside of that you run into potential overheads. And so in fact on ARCHER2 it would be unlike, the sweet spot is probably 16 MPI processors, each with 8 threads, probably at a first guess. Not definitely not 1 MPI processor, 1 to 8 threads, maybe 2, 1 on each socket with 64 threads. But again, there's a lot of complicated effects there. And the final thing is, as David just noted, on NUMA nodes, you need to make sure that MPI processors are spread across sockets, and the OpenMP threads on the same socket as their parent process. Not all batch systems do a good job of this, and so basically, one of the exercises, very early exercises, if you want to do it, is literally just to run a program which checks where these things are being placed. So not only do you have to worry about the combination of processes and threads, you also have to worry about where they're placed. And if you get that wrong, then your performance can be spectacularly bad. And unfortunately, there was a system change between 2 months ago and this month, and recently that changed the way that was done. So this is something which changes with time. So you always have to keep checking. Slurm changed their definition of what a socket meant. So 2 months ago, if you told Slurm to give you 1 MPI process per socket, it would have given you 2 processes on a node. Now, the definition is a socket is one of these 16 core NUMA regions. So it's something you need to care about. So I've wittered on for long enough. I'm just about on time. Does anyone have any questions about that lecture? What I'm going to do now is basically show you the exercise sheet and get started on the exercises. I want to I need a window on ARCHER2. I don't have one at the moment. Oh, is it the 4-core compute core? It might be, yes. Sorry, that's a good. You're right. Sorry, Cameron, you're right. It's not. It's down to the 4. Yeah. Sorry. Give me a second. They definitely changed it. So the question there is from Louise. Not yeah. Pure MPI using MPI plus code or MPI, for instance, the use of MPI. So unfortunately, that's problem dependent. Though, so again, it is. I mean, for example, it's quite difficult to predict. I had an MSc student this year who looked at a hybrid MPI+OpenMP version of. So Jin, yes, immediately and just when the practical session starts, we can do a screen share. So just to answer Luis's question, he wrote a hybrid MPI+OpenMP program of a very simple nearest neighbor halo swapping code. And on ARCHER2, he found that MPI plus OpenMP was quicker than MPI with about 8 or so OpenMP. But on a different machine, Cirrus, which is a different architecture, it was always slower. So, unfortunately, it's a whole bunch of combinations of algorithmic issues, software issues, and even hardware issues, compiler issues. Yeah, it's not obvious until you've run the code. That's one of the problems with MPI+. Does that answer your question, Louise? It was a good question. Yeah, it's not obvious. But having said that, on modern computers where the number of CPU cores are getting bigger and bigger and bigger, it's getting more likely you'll get a benefit. Let's put it that way. So I was not particularly. A smaller address space. Is that to do with caching, do you think? I don't know if that might be. Yeah. Okay. So again, I talked about NUMA effects, but there's also caching effect. One of the problems. One of the reasons why MPI works better. Yeah. So one of the reasons why MPI works better than you might think is that MPI is by definition cache friendly. It is impossible in MPI to access data that belongs to a different process's cache because you're in control of all your own memory. The reason when OpenMP starts to get slow is when threads access data which is cached by another thread, and that's when you get these weird effects. Bizarrely, pure MPI completely avoids that because by definition you cannot access another MPI process's memory. Yes, it might be. I mean, again, that's the problem. Not only do you have to keep investigating the balance of MPI threads and OpenMP threads and MPI processes on a new when you get a new architecture, you have to investigate it with time because, as you say, libraries and compilers change. So I'm sure if you're a modern software engineer, you'd have some wonderful continuous integration thing that runs this every night and gives you a graph in the morning of which is best. I mean, I'm being facetious. That actually is probably what you'd have to do. And it could be data set. It is very difficult. It is a difficult problem. I just wanted to sort of overview the exercise sheet, which is what I'll do is I will. I find it easier to share my whole screen, but I need to close some windows here. So so let's share the whole screen. So again, I have to, unfortunately, this is this annoyance of, whoops, I said the way that, let's move that off there. So this is the exercise sheet. So it's not entirely bespoke to this course, but basically what I've given you is I've given you a traffic model. Now, so I will maybe I've got a very simple traffic model code, and I'll explain what that is. And I've given you something called traffic.car. You can run it. There are some MPI exercises here, which are a whole bunch of stuff which you might be interested in. They're all to do with replacing this, like we did with the halo swapping example, replacing MPI send receive with different I send receive, non-blocking send receive wait, looking at barrier effects, and MPI neighbourhood to all. Then this is maybe not. Then I give you an OpenMP code which you can look at, and then the final one is hybrid OpenMP. But you'll see the first exercise of hybrid MPI OpenMP is to do with process placement, and this is basically there's a program called XT. So somebody asked about the placement of process, and it's really quite difficult to get right. There's a program called XT High, which all it does is print out where they're running. Say, hi, I'm rank 7, thread 5. I'm running on CPU core 53 of node whatever, and that is really useful because that you can read the Slurm manual till you're blue in the face, but I can never understand it. I just suck it into trying to see it. And then the final one is about the hybrid traffic model. So it's slightly freeform, this exercise, in that there's, I've given you a code, I've given you a C version of the, I've given you a MPI version of the code, an OpenMP version of the code. And I want you to, and there's a whole bunch of exercises here which you can do. I will do what I didn't do yesterday, which is to get the settings correct, which is hidden away really far down. This is me on ARCHER2. The reason I'm doing this is if you look at the web, where's my web, the materials, like many things, if you click on this code, it will download to your laptop, which isn't very useful, but you can just cut and paste that URL. Not the there's solutions in here as well. You can copy link, and then you can just wget. Oops, what have I done? On wget, it should work. And so what I would do if I were you is I would just hover over the link, cut and paste it, or you could actually git clone this repo, which some people do. The traffic model is very, very simple. I have a lecture which describes it. I think actually, well, yeah, I'll just basically show you a couple of slides from the lecture if I can find them. So this is a I'll just basically go back to my normal modus operandi, which is to not share the whole screen. So I'm not going to go, so hopefully you can see. This has got a lot in it, but the main point, and there's lots of stuff in here which isn't that interesting. But what we're saying, the traffic model basically is a cellular automaton model where we have a road which is a series of cells, and the cells are either occupied or it's the world's most simple cellular automaton. The cells are either occupied or unoccupied. Occupied is with a 1 and unoccupied with a 0. So I will upload these slides in a second. Sorry, I realized I didn't upload. The problem with these slides is there's lots of animations in them. So when I upload them, they look rubbish. Apologies. So I'd forgotten I hadn't uploaded these, but it's really just to explain the model. It's very, very simple. I will upload them after the lecture. Sorry about that. Yeah. And the model is, if a car can move, it does. If a car can't move, it doesn't. So each iteration, you say that car can move, that one can't, and that one can. And then they move like that. And this step, that car can't move, that car can, that car can. And they move, and then off they go. And basically, all you do, and this is lots of stuff here, which I don't have time to go forward, but all you do when you parallelize it is that you divide it up, and you basically have to do halo exchange between neighbors. And this was a diagram to show that. But you take the model and you parallelize it by splitting the road up. That's obvious, and you have to communicate. I just want to show the pseudocode. So this is the pseudocode. In the parallel code, you have to do boundary swaps because the state of a cell depends on its nearest neighbors. Okay, the state of this cell depends on whether that one is full. The state of this cell depends on what that one is empty or not. So you have a sort of a halo-based model where the state of each cell depends on the state of its nearest neighbors and itself. So you have to do boundary exchange halo swapping, which in this simple model is just a single value because it's a 1D problem. And the serial code is very simple. You have an old array and a new array, which is this time and the next time. You initialize the old array randomly with some density of cars, which I think is set to about 0.5. And basically, this is the main computational loop. Whoops. You loop over you loop, and this implements the cellular automated update. You loop over the cells. If the current one is occupied, if the next one is occupied, that it doesn't move, else it moves, the new one is empty. So that's the case of an occupied car moving forward. If the current one is empty, then it becomes occupied if there's a car downstream. Okay, so those are the rules, and then you copy back old equals new. So that really is the model. The only difference in the parallel code is that there is a halo swap up here to set the boundary to do the halo swapping. So I will very briefly show you the code, and then I'll let you. You can ask questions if you want, but that's the model, and it's really just there as an exemplar of a very simple halo swapping stencil-based code. But if I just go, oops, wrong one. Yeah, if I unpack have I unpacked it? No. You'll see there's a whole bunch of stuff here. There's lots of versions, C hybrid, C MPI, C OpenMP, C serial, F MPI, F OpenMP, F serial. There's even Python ones if you're interested. There's ones that have been refactored into more elegant code. This is from a bigger course. But if I go to the C MPI, if I go to C serial, you'll see it's very simple. We have a large road, we have an old road and then a new road. We malloc them, and then we initialize the road with a certain density, which is basically just over a half. It's called init road. And then we go into the update loop, which is this. We do update the boundary conditions, which in the serial code is just a copy. We have an update road routine, and then we do a copy back new to old, and we print how fast the cars are moving. And so this is very, very simple. This is the serial code. Update the boundary conditions, which is just, I should have said, it's a periodic simulation. So when the car moves off the right or the extreme end of the road, it comes back to the left. In some sense, it's traffic on a roundabout. But if you look at traffic lib.c, you'll see that the update road is just the code that I showed you there. That is exactly what the pseudocode I showed you. And the C again, you want to fix the C version, the MPI version. Sorry, I can't type. Is exactly the same. It looks very, very similar, except there's a bit of MPI in there. You allocate the road a local size, which is the total number divided by the number of processes, but the actual update is very similar. Well, the initialization is a bit different because we have to do it on a single process, but the actual, yeah, this is done. It's exactly the same, except we have, and I've deliberately done it with send receive because I want to do something better. But all we do is do a halo swap, and then we have update road, and then we copy back. So hopefully you'll see they're very, very simple. So basically you're sending a single halo element up the way and a single halo one down the way. So I know it's a bit of a rush through, but it's really a very, very simple code, 1D code, domain decomposition, where you have to swap boundaries at the two ends, and the exercises, there's a whole bunch of exercises there which you might want to look at. So so please play around. There's lots of suggestions on the sheet as to what you might want to do. As I said, the initial ones are more related to yesterday's lectures, which are to do with, basically looking at the performance, replacing MPI with send and receive. As I said, a whole bunch of stuff. These are all just suggestions. If you're brave, you might want to try this. Neighbourhood B you could use, and this is just then you can look at the OpenMP code. I should show the OpenMP code as well. The OpenMP code is very, very simple. Give me a second. Sorry, something weird just happened here. Oh, okay. I'm showing the C one here, but there's also the OpenMP is very trivial. It's just the serial code, but a couple of an OMP parallel 4 for the copy back, and the update road is parallelized. Traffic-lib.c. Update road is parallelized with a simple parallel 4. Default none shared, and when you update the road, you count how many cars have moved because you want to know what the average velocity of the cars is. So that's the reduction variable. So there's OMP parallelism in the two major routines. I think it's probably best if you have a look at the codes and then maybe come back with questions. And so what we'll do now is I can delete this. How do I delete? Okay, I'm having problems here. I'm not very good with this. Okay, I'm not doing very well here. I'm not really familiar with this this interface. Sorry. Okay, I'll have to put up a. I don't quite know how to delete this, but I'll be around till 11 to help with the practical. Remember that you'll see on the website there's a different reservation for today. That's on there's a different reservation for today if you want to run quickly in the reservations. And I will. Okay, fine. So that's the schedule for now. I will update in the break. I'll update, but I said the slides they don't look very good when shown as PDF because they're annotated. They're what do you call animated. But that's what will happen. Hopefully, you know, the exercise sheet there, and that will give you something to work on, a prototype code to look at, and you can play around with looking at the performance and such like. There's a lot of suggestions there. And Shin, we can maybe do a. Are you there just now? I see you're having some issues. Yeah, so what I'll do is I'll set up a breakout session just now, so me and Jin will disappear off, but we'll be able to screen. Can you just give me 1 minute, Jin? I take a break. I'll be back in 1 minute, and then we can do the breakout session. Hi everyone. Sorry for the slight mistakes with some of the settings there on the examples. I'll basically just is it okay? Is it okay to restart now? I don't know if people have so I thought that it would be worth is it working now? It's not muted according to me. Yeah. So okay, yeah, it seems like just. So before we look at actually one of the sort of previous exercise was to get to know the MPI code, the OpenMP code. But if you were looking at the hybrid stuff, the interesting part was to look at the process and thread placement. I'll just go through because that is something you need to get in your head, and it is one of the things which, and I'm sorry I made a mistake on it. So if I go to what was it, C hybrid, that's for example, and as you for some reason I put this in, but then I don't understand why this. Yeah, this used to work. I don't understand what's happened. But if we basically, what I'm saying here is I want 2 nodes. I want 32 tasks per node, and Slurm will have some, any batch system, but Slurm will also have some default way of placing them. And I really don't know what it does. So I try and be very specific. So what you do here is you say, well, I want 32 tasks per node, but I need 4 CPUs per task. So that multiplies up so that will space them 4 apart. So you'll get an MPI process on nodes on CPU 0, CPU 4, 8, 12, 16, whatever. Then, give me a second, I'll put the correct thing in here. Then you need to say, well, the reason I've done 4 CPUs per task is I want to use 4 threads. So I've set that here. You could actually do export OMP num threads equals $slurm CPUs per task if you wanted to make sure they were always the same. Actually, if you wanted to do, but all that Slurm can do is pin the processes, because it's Slurm that creates the processes with srun. It's at runtime that the threads are created. So how do you make sure the threads? Well, you have to do this. Export OMP places equals cores tells the OpenMP runtime system bind them to the cores, and that. So this should, and then you also have to say minus int equals no multi-thread, because the operating system thinks that the ARCHER2 nodes have 256 CPU cores. That's because each physical CPU core can run 2 hyperthreads or symmetric multi-threads, depending what terminology you use. But we don't need that for HP. We ignore that for HPC. So there was a lot of stuff going on here, but this is really just a kind of prescription. And let's check that this works. It's running. And let's have a look. So you'll see that this XD says so we're running on 2 nodes with 4 MPI, and that's nice. So we can see that we're running on 2 nodes. And on the first node, and we've got 64 ranks overall, but you can see this is really nice. Yeah, node 0, rank 0, but we get threads are bound to the cores 0, 1, 2, 3, 4, all the way up to 128. Just as we want, and exactly the same pattern on again on node 1. So that's what we want, and it's not trivial to get that, but this is a recipe which gives you the right answer. You didn't used to need this option, but you do now. Interesting to see what happens if you don't do OMP placed equals cores. Let's have a look at that. May or may not work. I mean, the problem is that you can see we've had to specify about whatever 7 or 8 options here. So there's hundreds of combinations of these options. Who knows what the corner cases are? But I know that this recipe works. But I said that the problem you have is that Slurm, at least in my view of the world, can only bind the processes which it launches. The threads are created at runtime, and that did work. Okay, that did work. So I'm a bit surprised at that. Okay. Yeah. Okay, that worked. That may be okay. So you don't absolutely need that. It doesn't look like to get the right binding. No. Okay. So but you should put it in. We can try other things. What happens if we don't do? Let's leave that in, but not do multi-thread. Let's see what that does. So you do have to spend, I mean, as I said, you can read the documentation until you're blue in the face, but unless you actually okay, so that sort of does what we want. Okay, that's interesting. That sort of does what we want, but the binding is here. Okay, so previously, oh no, it doesn't do what we want. Sorry, this is wrong. Fine. Okay, fine. What this has done is it has bound both thread 0 and thread 1 to the same physical core, but thinking they can use the hypercore. And the hypercores are numbered 128 to 255. So this hasn't done what we want. You'll see that if we go up here, we'll stop at 64. Yeah. So we're not using, so 63 and 191, or let's look at the first one. The way the numbering works in ARCHER2, 0 and 128 are the 2 hyperthreads of that, what we want to call them on the physical core 0. And so we need the hint equals no multi-thread. So you can see it's just a bit of a bind. This is again another trickiness. So I just thought that was a useful exercise to play around with. But what I'll do now is having sorry, I'm trying to find, as ever, I've run out of windows. Let us sorry, I'm sorry, apologies about this. So there are 4 styles. So turns out there are 4 styles of MPI+OpenMP programming, which are relate to where you make, how you interleave the OpenMP directives and the calls to the MPI library. And what they've done is, at least for some of these styles, the MPI library has to do more work. And so MPI now has a threading interface where you use a different MPI init call. You don't do MPI init, you do MPI init thread, and you tell it which level of threading support you want. So there was an extension to MPI. So the 4 styles are called master only, and this is, in fact, by far the most simple, simple approach. You basically take an MPI program and you leave the communications as they are, and all MPI communications take place in the sequential part of the OpenMP program, which is running on a single thread, the main process. And all you do is you use OpenMP to speed up the computation parts. And that's the simplest model, and it's what I would suggest you do for your hybrid MPI OpenMP traffic model, is literally to copy the MPI code and stick OpenMP directives in the computational loops. And that is called master only. And in fact, that probably needs no extra functionality in the MPI library, because the MPI library is being called in a serial region, just like it always was. Funneled is similar, but all MPI communication takes place with the same master thread. But this can be inside parallel regions. So that what it's saying is that all MPI communications in the entirety of your program are always done by the same thread, but that could be inside a parallel region. And that would require you in an OpenMP parallel region, which had an MPI call, to put something around it. So either an OMP master, or you, if thread ID equals whatever. So that would require you to update the code. Again, I can't see how the MPI library needs any additional functionality here, because it is still only being called once at a time by the same thread. Serialized is the next generalization, where only one thread makes MPI calls at any one time. So you could make MPI calls within an OpenMP region. In other words, threads can call the MPI library, but you make sure that only one thread makes the calls at any one time. That would require you, again, to put something like an OpenMP critical section, an OpenMP critical section around the MPI calls. Now, this is, you now need to be careful here, because you could have different threads accessing the same send and receive buffers. You need to be worried about race conditions on that. But the major problem here is that MPI is when you send a message in MPI, it's from a process to another process. So you are saying, please send this MPI message from rank 5 to rank 7. The problem is rank 7 will have potentially multiple threads calling receives. So you might have, imagine you've got 4 threads per MPI process, and each thread is sending a message. A single rank will be doing 4 sends, each from different OpenMP threads, and another rank will be doing 4 receives. How do you make sure that they match up as you expect? Because by default, MPI will just match on the process, on the rank. And there's 2 ways to do that. You could set up separate communicators, but the simplest way is to use tags. And that's what people typically do. Whenever you send in a message from a thread, you tag that message with the thread of the sender. And then when you receive a message, you specify a tag for the, again, to match the tag of the sender. So again, if MPI were defined today, this probably wouldn't be needed, but threads were retrofitted onto MPI. And this is one of the prices you pay. You cannot send a message from one. You cannot natively send a message from a particular thread on a particular rank to another thread on another rank. You have to do it by hand, and you do it by hand by matching up the tags. Again, it's not clear that the MPI will need to have any extra functionality in it, because it's only being called. The MPI library is only executed once, any one time, albeit by different threads. So you, as the user, will have more to worry about if you have multiple threads accessing the same send or receive buffers, but the MPI library probably doesn't. The one where MPI has to do a lot of work is multiple. What you're saying here is I can call MPI from any thread at any time. And so you could have two threads calling the same MPI library at the same time. That requires the MPI library to have threading support. At the very least, for it to, so basically, the MPI library will have internal data structures for monitor its queues and such like. If you have two threads updating the same queue at the same time, then you're going to get undetermined results. So at the very least, the MPI library is going to have to have blocking or mutexes around to make sure that multiple threads don't access the same queue at the same time. And some implementations may not support this. Unfortunately, those that do support it don't perform very well. The reason being that the way that people have done it is they simply put lots of locks in to the existing MPI library. And that means that although you've called it at the same time from two threads, they're basically, it's operating sequentially. So master only funneled, serialized. Master only funneled, I'm sure don't need any extra work from the MPI library. Serialized, I would expect doesn't, but multiple definitely does. And unfortunately, historically, simply by asking for a thread-safe version of the MPI library by thread multiple, you get poorer performance because of all the locking in the library. So OpenMP master only is very, very simple. You have some work, you have an MPI call, you have some other work that's in the non-threaded, but all you do is you put parallel directives around the work regions and they go faster. So MPI knows nothing about the threading. All that happens is that at runtime, the computation goes faster. Okay, so do you mean? So in the master only, all MPI communications take place in the sequence part of the OpenMP program. Oh yes, the conclusions. Yeah, the conclusions are that master only will require no additional functionality from the MPI library. Okay. Funneled, I can't see how it does need any additional functionality in the MPI library. Serialized might, but I don't see it. Again, the problem comes where the MPI library was written to be run by a single thread at any one time. The problem comes when you have multiple threads calling the same MPI library at the same time. So the MPI library may be updating queues to say, oh, there's a new message coming, I'll insert it into this queue, and might be a foreign receive or something. If that is done by two threads at the same time, unless the MPI library has been extended to be thread safe, you could get rubbish. And so definitely, if you want to program in the multiple style, you have to tell the MPI library, could you please give me a version of yourself which supports the multiple style, i.e. multiple threads calling it at the same time. There will have to be extra functionality in the MPI library. And unfortunately, what people have probably done, because MPI libraries are very complicated and were written to be serial, they just put lots of locks in. So they make sure that, you know, two threads are never doing the same thing at the same time. But they're basically, there's lots of synchronization within the MPI library. So definitely, if you instantiate a version of the MPI library which supports MPI thread multiple, then the MPI library has to do a lot of work to support multi-threading, and is in practice a lot slower. Does that answer your question? So my conclusion is these three probably have no intrinsic overhead, but this does. You could do that with a simple benchmark. So master only is very simple. You take a serial program, you leave the MPI as is, and you parallelize the work. And that is how I would recommend you do at least the first version. That's how you do your. No, you want threads to share an L3 cache actually, because you know when threads shared. So basically. the equivalent of halo swapping in the OpenMP code is that a thread reads a value of the array which was being updated by another thread. Okay. Now, the problem, OpenMP becomes slow when you're accessing data which isn't in your own cache, because there's lots of cache coherency. So actually, you want them to share an L3 cache. That's by that. You could play around with different placements and mess that up and see. But yes, I would expect that is exactly what you want. You want them to have their own cache, so that if two threads have to exchange data, they only have to go as far as the L3 cache, which is fast. They don't have to go all the way out to main memory, at least. I think on ARCHER2, the L2 cache and L1 cache are both shared by a same code. I think there's any sharing of L2. OpenMP funneled is the same code, but basically we have, okay, so now so if you'll see here, we ended the parallel region before the send and started the parallel region. So we had fork, join to a single thread, fork again. Funneled is you have a parallel region which extends across the whole, I'll do it here, across the whole, so you have multiple threads calling this code here, but you have a hash private OMP master, which in OpenMP says only thread 0 calls this. Okay. However, you need to be careful, because you need a barrier before and a barrier after the send. It's not immediately obvious why. Can anyone think why? So let's assume that this work, okay, here is updating the data that you sent here, so that this send depends on the work, and this work here is reading this data. So this send depends on this work having been complete, and this work depends on this send having been complete. Okay. Why do you need a barrier before and a barrier after? It's not obvious. This is already quite a simple code. You need to know a bit. Anyone guess? This is an OpenMP question. If you've not done OpenMP, it will be Greek to you, but make a guess. So David, yes, that's the answer for the this barrier here. Whoops, sorry. Master only funnel. This barrier here is required because otherwise the worker threads here will. So master says. So yes, exactly. So that's good, right? So the barrier before is the more obvious one. That you're saying, I'm going to send data which is being worked on by all the threads. I therefore need to wait for the barrier for that work to be complete. However, master says thread 0 does the next work, but master does not have a barrier at the end. And so what could happen is that all the work's finished, the master starts sending the data, but thread 1 goes on and starts working on it before the data's arrived. Or actually, yeah, or maybe I don't have a receive here, but you want to send the data which was worked on here, and not up. So actually, if you without the barrier, a thread could start updating this data while it was being sent, and you would get indeterminate results. In a real code, you'd have a receive in here as well. But yeah, okay. So yes, that's correct. The barrier before is to make sure that the buffer is ready to be sent. And the barrier after, because master doesn't have a barrier at the end, which isn't obvious, but it doesn't. So already, even this very simple funnel model, we're starting to get these slight issues. Serialized is basically you have some work, and you have sent. Now here the send has to depend only on the work done by by a particular thread. Okay, this makes sure that if thread 2 does a send here, thread 2 has completed the work. But this requires a model where this send is only dependent on work done by the same thread. But what you have to do is you have to put a critical region, and the critical says every thread does this call, but only one at a time. So there's a lock effectively around this, and so that means that the MPI calls happen serially, sequentially, I should say. They happen sequentially. And again, I haven't put barriers in here, but again, this would only work if the send data here is only operated on by the thread that does the send. So you'd have to be careful about that. OpenMP multiple is just basically you do some work, you do a send, you do some work. And the point here is this code looks very simple, but so what you're doing here is you're saying to the MPI library, look, I'll take care of any race conditions, okay? Trust me, I'll make sure that only one thread is calling you at once, okay? And so that is where you have to do a master region here or a critical region here. In this model, you're putting all the work over onto the MPI library. You're saying if multiple threads call you at the same time, it's up to you to sort it all out. And that means the MPI library has to put in things like critical regions and stuff like internally, which will slow it down. And so, yeah, those are the models. I'll go back. Master only, funneled, serialized, and multiple. So making MPI libraries thread safe is difficult. You have to lock access to data structures or have multiple data structures, one per thread. It requires significant overheads. And the worry is that, so, you know, you'd be quite annoyed if someone said, okay, we've just updated ARCHER2 and now the MPI library supports OpenMP. You'd be quite annoyed if your code which didn't use OpenMP went slower because of the overheads of ensuring of thread safety. And so to get around that, so as not to hamper the performance of single-threaded codes, at initiation time, you say what you want. So what you say is you replace MPI init by MPI init thread, which is I think it's a strange terminology. And what you do is you say what level of thread support you want, and you get back a level of support provided. So what you do is you say MPI init thread, the usual horrible arguments, and you say, I want this level of support, and you get back what it's providing. And that means that it may not be able to provide what you wanted. So you can ask for MPI thread single, MPI thread funneled, MPI thread serialized, or MPI thread multiple. And these are guaranteed to be increasing in number. So that will be 0, 1, 2, 3, for example. So you can check. What you should do is if provided is less than required, then print I can't do anything because this library is not providing the thread support I need. So that's what you should do. MPI init thread. This is what I require. This is what I get, and then you should check whether you're happy with that. So as I said before, thread single, only one thread will execute. Thread funneled, the process may be multi-threaded, but only the main thread will make MPI calls. Serialized is again multi-threaded, but only one at a time. MPI calls are not made concurrently from two distinct threads. All MPI calls are serialized. So for these three models, you're telling the MPI library, and it's up to you not to break this contract, but you're promising the MPI library, I will not call you twice from different threads. Here you're saying, I'm going to call you as many times as I like from different threads. It's up to you to sort it out. And they're monotonic, so thread single is less than thread funnel, is less than thread zero, less than MPI thread multiple. So actually, yeah. So there's a slight confusion. Well, there's a slight complication here that the MPI library is designed to designed to work with any threading model. That could be POSIX threads. We're talking about OpenMP here, so some of the terminology is not completely consistent. So, for example, there's not any distinction here between master only and funneled. Yes. So yeah. But I mean, I think that in my experience, if you're going to do the master-only model, then you don't actually even need a thread-safe library. To be honest, I'm a bit naughty. When I write master-only codes, I just use MPI-init. I don't use MPI-init thread, to be honest. So technically, if you're doing the master-only model, you should really initialize with MPI with the funneled style, because that means that the process may be multi-thread, but only the main thread will make MPI calls. So the issue is that the library is MPI library is written for general threading, and we're talking about OpenMP here. But that's a bit of a technicality. I don't think it's a big issue. So yeah. So you can do things like query thread to work out what the current level of thread support is. And so what you should really say is, if provided is REST and requested, print not a high enough level of thread support and abort. And that's what you really ought to do. I have to say, I have to ask my colleague Mark for which MPI libraries currently support MPI thread multiple. I mean, MPitch and OpenMPI do. I think most of the major ones do now, I have to say. I've not seen a problem in practice, but you should do this when you write your codes. So we're going to come along to a few advantages and disadvantages of these different models. Master only is very simple to write and maintain. There's a clear separation of state between communications which are done serially and computation which are accelerated with OpenMP. There's no concerns about synchronizing threads before or after sending messages. So it's very, very simple. It's definitely your first port of call. However, threads other than the master process are idle during MPI calls, which could be an issue. The other problem, something of a technicality, well, it's a technical issue, but it can be a big problem, is that all communicated data passes through the cache where the master thread is executing. So, you know, one of the ways, the only reason that OpenMP is mildly efficient is that when threads operate on data, they cache that data in their local caches and don't read the main memory. The problem here is that you're going to be bringing all the data back to the cache of CPU 0 and then possibly having to send it back out again. So that is potentially a problem. That's not an issue, though. That's not so much an issue if you have small numbers of OpenMP threads, which, for example, all share L3 cache. That wouldn't be such a problem there. Inter-process and inter-thread communications do not overlap. There's a complete distinction between the two. Your synchronization is done through parallel regions, which are relatively high overhead. And if you want the packing and unpacking of derived data types, which is done by the library, is done sequentially. There's no threading there. But it is by far the simplest model, and it's the only one that I've ever actually used in anger. Oh no, that's not true. That's not true. Sorry, it's the one I've used most in anger. Here's an example. Is that if you have an OpenMP, an MPI code, okay, you could hope that you're doing lots of sends here, okay, an asynchronous send and a receive. Some of these sends will be within the same node, and some of the sends will be between nodes. They're all happening at the same time. So internode and intranode messages are all being sent off and received at the same time. If you do a master-only style, what happens here is you do a parallel do there, and a parallel do there, okay? And the inter-thread communication happens here, implicit. So when I say communication, I mean accessing different non-local elements. And there's also a barrier here as well after the parallel do. And so there's extra synchronization, but also this only takes care with internode communications, and the thread with communication within a node happens through OpenMP. So again, that could increase your overhead. So the important point here is that this is accesses AI and AI minus I minus 1 different sections of the same array. Funneled is still relatively simple to write and maintain. You've got these cheaper ways to synchronize before and after message transfers. That's using barriers rather than starting and finishing parallel regions. And also possible for other threads to compute while the master is in an MPI call. And so there is a chance for you to say, right, okay, I'm doing an MPI call, but there's other work I could do because the other threads are still active. Disadvantages are, of course, it's more complicated because there's this less clear separation between the different levels of parallelism. There's still this issue of all the data passing through the same cache. And again, inter-process interthread communications still do not overlap. Where I have done funnels before, it's an interesting point. I said that although you logically think in your head of non-blocking communications happening in the background and therefore overlapping with communication and calculation, in practice, because the way the library is implemented, that often doesn't happen. What you can do here is you can genuinely overlap communications and calculation. So what you can do is you can say, I will have, say I have 8 threads. I will do a funneled model where thread 0 only does communication, okay? And the other threads only do calculation. And so there you can actually overlap communication and calculation because you have a separate thread dedicated to doing communication. So that is a model which I know my colleague Mark is looking. I've tried it in the past and had limited success from it. We're looking at that again because on a machine like ARCHER2 with so many CPU cores, that might be a way to do it. So what you do is you basically dedicate of your n threads, you dedicate one of them, thread 0 probably, to doing nothing but communication and use the other ones for calculation. And that's an interesting model. And you don't even need to use non-blocking communications because the thread which does the communications can do blocking calls because they're happening completely independently of the other threads. So that is a model that I've used. So OpenMP funneling, okay. So basically we're saying, what I said here, hashtag OpenMP parallel, got some work, have some barrier, and then you say, well, okay, what I want is I want thread 0 to do the communications, and I want the other threads to do some computation. The problem here is that you cannot use work sharing here. You cannot do hashpragma OMP4 because an OMP4 will want to distribute the work across all the active threads. Here you want it to be all except one. So you have to do your own you have to do the work sharing by hand, which is not rocket science, but awkward. But basically, this model I have used, and I have in test programs seen very good overlapping of communication and calculation, but never been able to reproduce that in a real application. But it is an interesting model. The other problem here is, well, what you can do is you can use nested parallelism, where you can say, this says I want a parallel region with 2 threads. This is sort of relates to what someone said before. You can specify a number of threads individually. So there's 2 ways of getting funneled with overlapping. One is to have a single parallel region with n threads, and by hand, say thread 0 does the communication, the other threads do the calculation. The others to be more sophisticated and use nested parallelism, where at the outer level you spawn 2 threads where one does the send, and the inner level you use nested parallelism to split this remaining thread 1 across other across the other computation. Again, this relies a lot on a very efficient OpenMP implementation, and we've seen problems in practice with this approach. Serialize, we said it's easier for other threads to compute while one is in an MPI call, and you can arrange for threads to communicate in their own data. So for example, if you're doing a halo swap of a large halo, you could have different threads communicating different sections of the halo. Again, it starts to get harder to write and maintain. There's lots of small messages. And once you do serialized, you have multiple, you still have this problem that although only one thread is calling the MPI library at any one time, you still have messages coming from different threads, and therefore you have to distinguish which thread receives which message, and you then need to use something like different tags. So this becomes complicated. So as I've mentioned this before, a call to an MPI receive just matches on the rank on the process, not on the thread. And the standard thing to do is to use tags. You could put all the threads into different communicators. You have communication for thread 0, communicator for thread 1, but that would only work if thread 0 on rank X only ever communicates with thread 0 on rank Y. If you want to have different threads communicating, you would want to use the tag. I've never done the communicator trick in practice. I've always just used tags. Multiple, you have advantages in different threads can in theory overlap. And so in principle, you can have lots of messages being sent at once. However, in practice, most of the MPI implementations just serialize them internally. And it's easier for you because you don't have to worry about synchronizing threads, but you've just passed that responsibility to the MPI library. So it's hard to write and maintain. Not all MPI implementations support this, and most implementations don't perform very well. Again, if MPI were designed today, it would probably support threading from the bottom up, and the multiple wouldn't be an issue. But because it's been retrofitted, it is an issue. So MPI+OpenMP is becoming standard. There's a statistic that 30% of consumed CPU hours on Archer. This is the previous system. That actually meant that 30% of the CPU hours were consumed by codes which were capable of MPI+OpenMP. We assume that stupid people did that. Many people have said this is the only way to exascale, like most people used to be saying, but that does require MPI thread multiple to reduce the overheads, and that doesn't, in practice, doesn't perform very well. Correctness is hard to achieve because of all the race conditions. Performance is hard to achieve because the entire application has to be threaded, and you still have this optimal choice of processes and threads and the placement on numerous architectures. So there's a lot of pros and cons there, but you know, think carefully before embarking on this route. Why, if you have a good reason why you expect it to go faster or to be more efficient, then off you go. Remember Andal's law: just because your kernel goes fast doesn't mean your whole code will. I'll come back to that. However, what I would say is that retrofitting OpenMP into existing MPI code can be challenging. However, if you write the code from the outset as being a hybrid MPI+OpenMP, then you can have a much cleaner solution. It's a bit of a, but I think retrofitting could be a lot of work. Even given a good hybrid MPI+OpenMP solution, achieving optimal performance can be a lot of work. It can use a lot of system-specific flags and settings. We've already seen that just getting the slurm settings is non-trivial. So you do have to worry about getting all your ducks have to everything has to be going well. And the reason I meant before is that I have this loop here. Imagine you have a code, and this function takes up 95% of the time, and this function takes up hardly any of the time. You give this function to your colleague, who goes away and writes a very fast hybrid MPI+OpenMP implementation of this kernel function, and it goes fast. The problem then is, if you don't also parallelize this function, which previously didn't take much time, it'll execute on a single process. So just because your main computational routine goes faster doesn't mean your whole code will, because you're going to have to add OpenMP into all the sections of code, even those which previously were running quite happy in pure MPI and didn't take that much time. So as from a code maintenance point of view, it's quite a lot of work. So I would say that basically of the 4 styles, I've used master only, and I've used funneled, where I identified a separate MPI, a separate OpenMP thread to take care of all the MPI communications. But I have not in practice played around with serialized and multiple, although I have had MSc students doing it, and this can be very tricky. So that's sort of the end of that lecture. You know, the exercise I think, which would be interesting if I look at the exercises. So technically, yes, Luis, you're correct. If you use the master-only model, technically you need to call MPI init thread with MPI requires MPI thread on. Yes, technically. In practice, I haven't done that because I just call it, it's a bit naughty, I just call it MPI init. Because I think that if you do MPI init thread with MPI thread funnel, I don't think that the MPI library has to do any extra work. So you're absolutely correct. Technically, that's what you should do because the standard says if your main program is multi-threaded and only a single of those threads makes the call, you should do MPI thread funnel. But with OpenMP, we know that actually the calls are taking place from strict serial regions. So yes, technically that's correct. In practice, that's not what I've done. It's a bit naughty. I would suspect there would be no performance difference between the two. Yeah. Does that answer your question? Your statement is correct, yes. But in practice, I suspect you get away with just good old-fashioned MPI init. What I should do is take a code. As I said, so let's go to the let's show. Sorry, I've got the wrong. Oh, okay, so you're saying your model is MPI thread master, but when you initialize it, you initialize with MPI thread multiple. Is that what you're saying? I don't think you should do that because what you're doing is you're then instantiating an MPI library which has a lot of internal locking and such like, not using it. So I would run with MPI thread funnel. That'll be a good benchmark actually. Yes, I understand. Yes, I would change the code now and do required as MPI thread funneled. And I suspect the code could go faster. I can't guarantee it, but I suspect it might. It depends on the MPI library. It definitely shouldn't go any slower. Yeah. Okay. I am sorry. I misunderstood your question. So you should always request the lowest level of support you require, because the higher level of support you require, the slower in principle the more work the MPI library has to do, and therefore the slower it could be. Okay. Now I understand your question. That's a good question. It's a good question. So fine. So I've lost the window. I cannot. My small brain can't cope with all these windows. There we are. Sorry, I'm back in the correct window now. So I think that if we go back to I was trying to share the exercise sheet. So this was the first bit, which was to look at the thread placement and play around with it. And then if you want to do the hybrid traffic model, as I said here, are you seeing this? I'm just checking. Yes, you are. It should be quite simple to add OpenMP ARCHER2 with the MPI code to make a hybrid code using the master-only model. Parallelize the computation update road and the code back in main, exactly as in the pure OpenMP code. So it's literally it's like 2 or 3 minutes of editing, and you should be able to leave the MPI communications as they are. And now there's a restriction in the code that it assumes that the road size is exactly divisible by the number of processes. It doesn't check whether that's true. It's a bit naughty, but it would be interesting to do that and then compare the performance on these on 2 nodes with total function scores. You could use all these combinations, and that would be interesting to look at how that works. Unfortunately, you probably have to run them all in separate batch jobs because there's a different setup for each one. I yeah, I don't know. I don't have. I should do this. I'm not 100% convinced which of these is fastest. I have to say, but I will have a look at that. Have a look at that. So that was that's the exercise. It's a very, very simple model. It's just to get you up and running and playing around with it. And I'll do a few experiments here as well. But the way it works is we've got the rest of the session till 1 is meant to be a I'll get this. Practical until 1300. So yes, so the idea is that we've got a practical until 1. I'm happy to hang around to help, and then lunch break, and then the final lecture after lunch is going to be the MPI shared memory model, and you'll see that in the exercise sheet there, the shared memory exercises are at the end as well. But I do provide solutions for those. So you're welcome just to look at the solutions if you want to. I'll probably just do that. Okay, so I'll be on hand just now. But I'll leave that up. I'm on hand. If you post any questions, I'll get the notification. But whether you want to stay on to the practicals or not, I'll speak to you again at I'll see you all at 2 p.m. Regardless of what. So yeah, it's up. I would say that it's kind of the model was to be so basically, yeah, sort of familiarize yourself with the MPI. But yes, I would say that as long as if you're happy with how the MPI and the OpenMP work individually, then I would work on 5.1, 5.2. Yeah. I mean, if you're not, the reason I'm slightly equivocating is some people may not be that what's the word? Familiar with OpenMP, and in that case, the pure MPI exercise are things you might want to work on as well. One thing actually that I didn't, well, I will just actually do a quick share very briefly. Sorry to hog the. You'll see there's an awful lot of stuff here. Okay, so the CMPI refactored and FMPI refactored are just versions of the code which are written in a more elegant way, and they try and hide the MPI calls from the main program using libraries and such like. They're probably not that interesting. The one which you might be interested in is CMPI deep. So there was a question there. So so basically, in the OpenMP model, yes. So there was a mistake, Lorenzo. You have to replace. There was a mistake. Sorry, there's been a change in behavior. Sorry. There used to be a -s flag to module load, which instead do it silently, and that seems to have disappeared. That passed me by. So Would that maybe, Lorenzo? I think that will probably fix the problem. Does that make sense? Yeah. Sorry about that. That was something I wasn't aware of. The deep ones. If I go to see, you'll see that the way that the standard code works. This is just an MPI trick. It's nothing to do with hybrid MPI and MP. If you swap halos of depth 1, then you do an iteration. You swap halos of depth 1, you do an iteration. If you think about it, if you swap not just the boundary cells, but the 2 extreme boundary cells, then you can do 2 iterations before you need to communicate. So instead of calculating every iteration, you communicate twice as much data, then do 2 loops. So you're trading off latency for bandwidth. The idea is that it's to communicate 2 elements of data with 1 send is better than communicating 1 element with 2 sends. And so if you look at the way it works, traffic.c, can't remember how generally I wrote this, but what it does is, so there's lots of debug. Apologies, there's lots of debug code in here. Apologies about that. Yes. So what this does is it basically it does the halo swaps every 2 iterations. So do swap is iter percent 2. It only updates the halos every 2 iterations. But if we look at the library, when it does it, it sends and receives 2 integers. Okay. So it's basically sending and receiving the 2 extreme values, not the 1. But then that allows you to do 2 iterations, which is basically that's update road. Okay, is I don't understand. This doesn't look like it. I'm sorry. Apologies. I may have distributed a. Oh yes, sorry. Okay. So yeah, you only do the swap every 2 iterations, but you update a different section of the road each time. Yeah, so that's what it's saying. Sorry. So this is saying that you basically only do every other iteration you swap 2 halo values, and that allows you to do half the number of communications, but with double the amount of data. And that may or may not have benefits. I apologize for this debug code. I obviously gave you a working copy where it's all commented out. That may or may not have performance benefits. Okay, that was just, I'll shut up. That was just a quick. Hi everyone. So that's the lunch over. I'll just. So I saw. Sorry about that issue with. I saw that issue with the if rank equals 0. I just assumed that I'd done something weird in my code and thought maybe I would, that maybe it was just some strange effect that I was seeing. But clearly, yeah. So basically, before the if rank equals 0, I got everyone to print their rank, and everyone said I'm rank 1, I'm rank 2, I'm rank 3, I'm rank 4, I'm rank 5. And then within the rank 0, I got them to print their rank. They said they're all rank 0. Made absolutely no sense. Sorry about that. I really don't understand. Really understand what was going on there. That's unfortunate, actually. That shouldn't happen. That was in C. Yeah, so it was a C issue in the foreshore. Some weird compiler bug, very weird. I will report it. I thought I was going mad, like most people did. Sorry, it's very. I really didn't understand what was going on there. So sorry about that. What I will do is if I can actually, where are we going? I've lost my windows. So for this afternoon, we're going to do it won't the lectures won't take this long, but a comment there. So then, oh, okay, yeah, okay, that's interesting. Okay, I just did OpenMP and it worked. Okay, that's interesting. It just seems to be some bizarre. Yeah, that's what I would assume, because O2 is kind of the default. Actually, it tends to be the default for on the on ARCHER2. So it's very strange. I will report it. I don't know if it's possible to. Well, anyway, it's very, very strange. I assume anyway. Yeah, it's very strange. Sorry about that. So I'm gonna maybe about an hour at lecture, and then the whoops, I'm in the wrong window. Lunch has thrown me. I'll give a bit about the remote memory access and the MPI model, and then there's an exercise you can look at, and then you're welcome to hang around after. Sorry, I'll be around after coffee if you want to finish off the exercise and answer any questions. Someone asked me, and I can't remember who it was yesterday, for an example. I'll just pre-post this just because you might want to look at it. Somebody asked for an example of using shared memory to have a single lookup table per node. That was something I posted on Stack Overflow, which I think, okay, that Stack Overflow link I think that's actually what you need, to be honest. I think that does what you want. Have a look at that. But have a look at that. Okay, so what I'll do is I'll give these lectures. So, as I said, I'm not a massive fan of the single-sided interface on MPI, which is put and get, remote read and write. However, we need to cover the basics of that to be able to understand how to do what I think is more akin to the sort of flip side of doing OpenMP, which is doing having effectively shared arrays in MPI. You need to know the basics of the put and get model to understand that. Particularly, specifically something called windows, the way that windows work. So apologies while I into RMA. Fine, sorry, I just couldn't find the. Okay. So share right window. Sorry, I'm finally there. Sorry for the delay. Just 5 minutes late. So as I said, I'll skim over this a bit because I mean I'll go over the material, but it's really I'm not a massive fan of this model, but it's useful to understand. So I'll try and keep to time. So why are people interested in remote memory access? That's direct read and write. Okay, what was this? Sorry. Okay, fine. Some terminology is something about the way that you write a program, and I'll give a bit about RMA, but I'm more interested in the management of windows and fence synchronization, because those are the two concepts which feed forward, and we won't do a particular practical on this. So what are the MPI remote memory access concepts? Well, the idea in normal MPI, if you want to transfer data from the memory of one process to the memory of another, this one guy issues a send, and this guy issues a receive. Now, what people what sometimes would be useful to do, and this is for various reasons, is to be able to do effectively a send without a receive that's directly write into a remote processor's memory, or directly read from a remote processor memory. So that's effectively doing a remote write with no matching receive, or you could do a read, which that would be doing like a receive with no matching send. And that you can do that in MPI with certain restrictions, but there are two main restrictions. One is, well, synchronization is now a major issue. We'll talk about that. But the other issue is to make it safe. When you do send and receive in MPI, the receiver specifies the receive buffer. The receiver is in total control of where the data goes. In this model, you can imagine a process writing to another process's memory. You don't want to be able to scribble over the whole of the memory. There's a concept of a window in MPI, where what processes do is they make windows of memory arrays available for remote memory access. You're allowed to do memory access within this region, and that allows you some error checking. The runtime system could say, look, you can't write to that location, it's not been exposed properly. So that's kind of how it works. Why extend the basic message passing model? Well, many networks actually support RMA in hardware. Across the network in hardware, you can write directly to or read directly from a remote processor's memory over the network. That's true of InfiniBand, and it's true of things like the Slingshot internet. Of course, this is the fundamental model for shared memory systems, OpenMP, read and write. And what happened was people said, well, I'd like to be able to do that. I don't want to have a send and a receive. I want to just directly write or directly read. And so people started to use these lower level protocols, and that led to non-portable applications. People were using low level system specific library calls. So that's the hardware. The hardware supports it. People say, why can't I do it? Why do I have to post a receive if I have a send? Why can't I write directly to the other process's memory? Also in software, many algorithms are naturally single-sided. What it means is if you're doing a sparse matrix vector operation, you have to gather data from lots of processes locally. You know who you want to gather from. You know it from the structure of the sparse matrix. I need to gather the data. But unfortunately, you have to tell the other process to receive it, to send it to you. And that's not so much of a big deal if the communications pattern is static. But if the communication pattern's changed, every time you want to read data from somebody, you have to tell them to send it to you. Wouldn't it be nice if you could just directly read and not have to tell them, you send me the data and then read it? There's an overhead to that. So one side, there's a number of terms for these. They're often called one-sided communications as an interface to remote memory access. It's slightly confusing because actually you have to have explicit synchronization, which means it's not one-sided. But one-sided means that if you do a remote write, it's called a put. Only this processor issues the write call, or if you want to remote read, only this processor issues a get. It's one-sided in the sense that as a counterpoint, the MPI normally be two-sided with send and receive. So it's a natural fit of some codes. It can, in principle, provide a performance scalability increase for many codes. However, it's not a silver bullet, and unfortunately, because MPI strives to be portable and robust, a lot of the overheads involved in making it work properly in MPI, I mean, you don't get very good latency, which is what you'd hope. So it's not a silver bullet at all. So the terminology, because the person making the call, because you can either do a put or a get, the terminology is the origin is the process initiating a request performing the call. Okay, so that's the person who does issues the remote write or the remote read, the put or the get. The target whose memory is being accessed by the origin, either remotely reading or writing. And so the origin is the one that makes the call, and the target is the memory who's being accessed. And the data can go from the origin to the target, or from the target to the origin, depending on whether you're doing a put or a get. All remote access is performed in windows of memory. This is to make it safe. You have to pre-set up. These are the areas of memory I am going to allow to be accessed by RMA. And all access calls are non-blocking. They're non-blocking. So when are they? So as with any non-blocking call, the initial call initiates the operation, but you need some waits later on to make sure it's completed. In normal MPI, you do an MPI wait on the request. What RMA does, at least the simplest terminology, is it has epochs. It has basically regions of global synchronization. So you say, I'm going to start doing remote memory access, you do it, and then you say, I'm going to end it. And within that start finish, everything is non-blocking, but it's guaranteed that after the finish, everything will have completed. And am I recording? I am recording. So the RMA program flow is you collectively initialize a window, everyone gets together and says, these are the areas of memory I'm going to allow to be accessed, and that's called a window. Then you start an RMA epoch, and that's a very technical term. The terminology gets crazy complicated, but basically the synchronization, think of it as a barrier. Right, we're all going to wait. Right, we're all ready. Then you issue communication calls, sends and receives. Puts and gets. And then you stop. And when you stop, all of those puts and gets are then completed. And then you can complete that many times. And then at the end, you can collectively free the window. So how do we get started with RMA? Well, window management, fences, and data movement are the three key areas we need to talk about. The first thing you do is you have to create a window. So what you do is you declare some memory as a normal array. Now, all this is just done in C. There is a fortran interface, but it gets slightly tricky. But the concepts are identical. The syntax is just a bit more convoluted. If you have declared an array with a malloc, which is your base array, okay? And what you want to do is say, I've got this local array. I'm going to make this array available within a window for people to read and write to remotely. So you create a window from it. So you've already created this data. You give the size, and these MPI ints are just basically long integers, 64-bit integers, because this could be bigger than 2 gigabytes or 4. You give it a size and see how big it is. So you might declare an array, and you say to MPI, look, I've got this array. It's a megabyte long. You give a displacement unit, which is a counting interval. So we'll see that when you do puts and gets, you will say, I want to read some data which is 1, 2, 3, 4, 5 counts into the window. What's the counting unit? Well, this is the displacement. And so if it's an integer, you'd say 4 bytes for the size of an integer. If it's a double, you'd say 8. This is there to allow portability between systems, again, where it's possible that two systems, it's unlikely, but in principle, you could have two processes talking to each other where one has 4-byte integers, one has 8-byte integers. It's a kind of a level of portability. Some information you can give, and this is extra hints which we'll not talk about, is collected across a communicator, and you get back a window which is of type MPI win. And once you've done that, this window is like a communicator. It spans all the processes, but it also has this. It defines a bunch of processes who have access to the memory, but it remembers what data you've given up. You can specify no memory. There's various technicalities here, but they're not particularly important for the basic understanding. So you declare an array, which is your window, and you give it to MPI. I said, make this into a window so people can remotely read and write to it. You can query them about various attributes and stuff. Isn't that interesting? And you can free them at the end. Okay, so you'll free them at the end. But typically, in the things that I've done, I have typically created the window at the start and freed at the end of the program. It's not something you do very often. So having done that, you need to be able to basically have a way of synchronizing and saying we're about to do remote memory access to this window, and you need a synchronization so that everyone's ready to do it and there's no race conditions. And that is called a fence. So the fences are the simplest way of doing that. A global synchronization phases alternate with global communication. So this is really, there are more complicated models, but this is everyone calls a fence, which is like a barrier. Then people do remote reads and writes, puts and gets, and they call another barrier, and they're all guaranteed to complete at the end. So you do MPI win fence. There are lots of assertions you can give, which are optimizations, but I'll talk about that, I think, in the next slide. Sorry. But with zero means, so basically MPI win fence, everyone's ready, the communication calls all go here, and then you have another fence. The RMA cannot be started until the first fence. All issue communications block here. The default value, there's no assertion, but all these communication calls, the puts and gets, are non-blocking here, and so they're only guaranteed to be resolved. This is like a wait all in some sense. So there's various, basically, one of the problems with the RMA model is it tends to be quite difficult to implement and tends to be quite slow. So the more information you can give to MPI, the more chance it has of optimization. So you can say things like, you can say, okay, fine. So when you do this MPI win fence, okay, MPI is by default going to go and check, are there any incoming writes to this window that need to be completed, okay? Is there anything incoming I need to wait for? But you can say, look, MPI mode no store. This window was not updated by local writes or any sorry, this local window was not be updated by. Anyway, there's lots of hints you can give here. For a performant program, you should give the hints which give MPI the most information, but in terms of correctness, you can just specify 0. So that's why in this thing we've said 0. So by default, you'd use 0, then you go back through and see if you could give more hints, but that's really performance optimization. So there are really 3 general calls, all non-blocking. There's a get, which is a remote read, a put, which is a remote write, and an accumulate, which is a remote write with like an addition at the end, if you want to increment the counter. So, so what you do here, this is like a send and a receive together. It's slightly, so basically you want to get, you're going to remote read, okay? This is the origin is giving the call. So this is like the receive buffer. This is where the data is going to go. This is how many. This might be an array, a local buffer, and you want to, might say 5 integers, for example. Then you have the target rank who you want to read from. You give the target displacement, which is how many elements into the target rank you want to read, and remember that is this is multiplied up by the counting factor. What was it called? Sorry, I'm very bad with terminology. Apologies. The displacement unit. And then there's that target count, how many you want to read, and a target data type, and then in the window. So this is basically like a receive. This is like the receive parameters, and these are like the send parameters from the target, but they're all put together. If you look, the prototype from MPI put is identical, okay, but here the data. So here the data goes from the window on the target rank to the origin address on the calling process. Here the data goes from the origin address on the calling process to a particular place in the window on the target. Now, sometimes you might want to add a number. You might have a shared counter you want to increment. If you do a get, then a put, that's not guaranteed to work. Remember, if you do MPI get to get the value, add 1 to it, and then MPI put to put the value, those are non-blocking, so they could actually happen out of order. So there's a thing called MPI accumulate, which allows you to add. So you have an MPI op. So that's a put, but the MPI op could be MPI sum. So that wouldn't just write the data, it would add to it, which can be useful. But the important point is that put and get, the prototypes are identical, but the data transfer is in different directions in the 2 cases. Just like non-blocking calls, you have to wait for synchronization until these are guaranteed to be complete. As I mentioned, the target displacement is multiplied by the window displacement unit, origin count, and target count in units of data type. It's very, very like a send-receive operation, except you specify the location of the window slightly differently. And there's lots of caveats here I'm not going to go into, but that's the basic model. So the basic model is set up your window, call an MPI win fence, so declare some data, put it into a window, do a fence, lots of puts and gets, another fence which completes them. And the reason why this might be faster is that MPI synchronizes on every pairwise send and receive. Here you could do lots and lots and lots of sends and puts and gets in here, and only a single synchronization at the end. So The plus side is you can reduce synchronization because the synchronization is under your control, but the downside is that it's harder to write correct programs because once the synchronization is under your control, then you can make mistakes. So basically, the generic simple approach: declare local storage on each rank, create a window including all the storage with MPI create, and you'll see that you'll notice that the RMA calls put and get didn't have a communicator argument; they had a window argument, but the communicator is implicitly stored inside the window. The important point is you can access the data in local storage using normal operations. Okay, so outside of these, whenever you're not doing puts and gets, you can just read and write to the local data like it was a normal array. So the array exists in a normal array, but when you're doing puts and gets, it is also part of this window. Synchronized everyone is ready, issue remote reads and writes, synchronized everyone is finished, and now you can access. So this might be a halo swap, for example, and then you can now access the data in local storage as normal. So here's an example, which is a slightly complicated example, which comes from a course originally developed by a colleague of mine, Nick Brown, and from a Cornell course. But what we've got here is we're basically going to do a broadcast. We're going to take data on rank 0 and broadcast it to all the other processes, but we're going to do it not with a broadcast, but we're going to get all of those processes to do a get to read the data. So what we do is we declare a window, we declare a control buff, which is of size 20, and that is the thing which is going to be broadcast, and my buff is the copy which is going to be read on each process. We create a window, and what we're going to do, it's a slightly asymmetric version here, but basically this window is only going to contain the data on rank 0. So you do a MPI win create, and everyone else who isn't rank 0 just says, look, I'm not supplying anything. It's a null pointer of 0 size. But rank 0 says, okay, I'm going to supply control buff, which is the thing I want to broadcast. It's 80 bytes long, size of int times 20. The counting unit is 4 bytes, size of int. That's saying if you ask for the third element of this window, I will go 12 bytes in. And I've just, the communicator is common, and I get back this window. So these match. So you have a window, but actually there is only data available on rank 0. And then after that, if rank is 0, initialize control buff. Okay. Now we need to do this win fence here. Okay. So now we're going to do a get. Can anyone think why we need the synchronization here? Why do we need that synchronization? Why do we need? There's a number of reasons, but what would happen if it wasn't there? So what's going to happen is after that, after this point here, if you're not 0, we're going to read the data from that array on rank 0. What would go wrong possibly if you didn't have the fence? Again, these are all things you don't have to care about in normal MPI because the synchronization is done for you by MPI. But I don't know if anyone has a... Yes, exactly. Rank 0 could still be initializing the data, whereas the other ranks are reading it, and you'll get garbage. Exactly. So this win fence is required to say, look, let's all wait until the data is initialized. Okay. We say MPI mode no proceed. That means that there's been no preceding RMA calls. And then we say, if I'm not ranked 0, I'll get data from into my buff, which is these are the kind of the receive parameters, which are 20 integers. Okay. From displacement 0 on rank 0, so that's start reading from the start of 20 integers, all within win. So basically that is effectively doing it. That's reading 20 integers, and this first 0 is rank 0, and this is saying I want to read from rank 0, and where do I want to start in that window? I want to start from the start, which is displacement 0. And then I do an MPI win fence. Without this win fence, these gets are non-blocking. It's only after the win fence that they're guaranteed to have completed. And we can say MPI mode no succeed. We're saying there's no RMA calls. There's going to be no RMA calls after this. This is very much somewhat gilding the lily, but out. And then if rank is not equal to 0, we can process the buffer, and then we can free the window. It's a slightly contrived example, but it does illustrate a number of concepts. So for example, what you could do and what I've done in the exercise for the traffic model is to make the entirety of the local array of the local road a window, and that allows, when you want to do halo swapping, rather than send and receive, you can directly write your data into the neighbor's halo, or alternatively read. Now, this is a, you could have done this not with rank, the non-zero ranks doing a get. You could have had rank 0 doing lots of puts. So because you have puts and gets, there's always a question of, do I get the end guy to get or the source guy to put? And it's a you could argue this is quicker. Of course, you should use a broadcast here, but you could argue this is quicker because if you do a bunch of puts, they're sequential, but these gets are done in parallel. Whether it's faster in practice, I wouldn't like to say. So there's a technicality here that that they're kind of being a bit pedantic here, but basically the idea is that that in principle, imagine there's a system where at the hardware level you can't do remote read and write to normal memory, only to special memory. In that case, there will be two copies of the window. One is in the public memory region, which is addressed by other processes. Another is the private memory. Okay, and the idea is that now there is no system like that. Okay, but this memory model is called coherent if updates to main memory are automatically reflected in the private copy consistently, or non-coherent if not. All modern systems are like this. There is not really any difference between shared memory, between public memory and private memory. It's just memory. So this is very much a technicality. They're just trying to guard against situations where the hardware is slightly weird. So MPI has two models. It's called the unified model if the public and private copies are identical, but the separate model if they're not. This is something of a technicality, so yeah, so I wouldn't get hung up above this. So I've never come across a system which wasn't the unified model. In other words, in all systems I've ever been aware of, if you do a put or a get, it doesn't go into some temporary holding space and is later copied into the target array. It goes straight to the target array, but it's just a technicality. So the reason that it's important is that to do the shared memory our MPI model, which we're going to talk about next, it needs to be the unified form. But in all cases I've ever seen, it is unified. So I wouldn't actually get caught up about that. So there is additional functionality. You can do point-to-point synchronization RMA. It's called the post-start complete wait. You don't have to do global synchronization, but it gets quite complicated. You can also do something called passive target synchronization, where you lock and unlock windows. But that's really well, this is actually a slide from an MSc course, but all I need you to know now is the basic model of creating windows, synchronization with WinFence, and puts and gets. And it's important to realize actually that this WinFence does two things. WinFence does two things, this WinFence. It's a synchronization in time, but it also completes all the RMA operations. Okay, so it's both at once. It's a synchronization in time, and it ensures that all the operations are complete. So the summary, the model is quite simple, but the syntax can be quite challenging. Performance may not be very good. These extra levels that MPI puts in to allow it to be portable and flexible mean that latency, which is what you really hope to reduce, may not be as small as you'd hoped. But Windows and fence synchronization are a key component of the MPI shared memory approach, which I am a fan of, which comes next. That was a bit of a rush through, but hopefully that makes some sense. Maybe I would just briefly, because we possibly have some time, I could show you. Oh, actually, this is, I did a, I did a run of the traffic model on 128 processes with 2 threads, 64. This is on 2 nodes all the way through, and the time was I don't think the time varied much. It's a very you could argue it went down here. No, I don't think it did. It's pretty. I mean, within noise, it's pretty flat. So, I mean, the downside is that for the traffic model, because it is so simple and has so little communications, we didn't see a big performance increase. But the upside is there wasn't a big performance. Problem. Yeah, we didn't see any. I didn't see any degradation of performance. So it was kind of both good news and bad news. What I really wanted to do here was just to show you I have a solution to the C. Sorry, I haven't got them yet. Sorry. They're in a separate tar file. Sorry, the traffic RMA ones. I just wanted to show you the solution. RMA/C MPI. And it's in traffic RMA.C. This is just the same code as the serial traffic model, but I've done the communications in a different way. So all this stuff is the same as before, except I need some new variables: a window, the win size, and a displacement unit. This is all the same as before, but now I have to publish. So this here I allocated them. I need to publish old road, which is the one where we do the non-local access on. So the win size is n local plus 2 times size of int, dispute its size. So I do MPI win create the old road. It's this size. The displacement unit is integers, and give me back a window. So that's fine. I do everything else the same as before. Neighbors are computed the same, and you'll see here that I've basically commented out the halo swaps here and done them with RMA. So I do an MPI win fence, everybody is ready, and I've decided to do the halo swap with puts. You could do them with get, but I've decided that. So what I do is I write my last entry, which is old road 1 local, which is 1 int, into the rank up at displacement 0 in their window, which is the 0th entry of their old road. And then I also put my first entry down the way into the halo, the upward halo of my neighbor down the way. And then I have to do a win fence again to complete that. So I thought that's a great. There's no reason to assume this would actually be faster, but I wanted to leave it in as a comparison to the existing code. So that's there for you to look at. There are some, yeah, okay. So that's the in Fortran. I just think it says Fortran programmers. It's exactly the same. There's really no difference. Same idea variables here. I don't think there's any difference in the syntax. Using MPI type size because there isn't a size of. It's all the same. Yeah, it's exactly the same in Fortran as C. Yeah, just exactly the same here. Yeah, exactly the same. Except it's a 0 1 1. It's the same. Okay, so I'll just the final lecture now. Apologies, it's a bit lecture heavy, but the final lecture is going straight on to looking at the yeah. Yeah, this and then more. Oh. So it's quite a short talk. MPI process behaving as threads. I'm using the traffic model as an example here. So the motivation, we're going to talk about node local communicators, shared window allocation, and synchronization. So the motivation is, we've seen this diagram in OpenMP parallel region, all threads access shared arrays. But the problem is that outside of these OpenMP parallel regions, you're in a sequential region. Why can't you just decide that at a certain point these MPI processes behave like threads and that they can have shared arrays? Well, that's what you can do here. And okay, this is my concept of MPI plus OpenMP. When you do MPI plus OpenMP, you have a pure MPI code. Then you underpopulate the node, so you're running on only running on one process per node or fewer processes in the CPU cores. So you take a performance hit, and then as you go through developer time, you add more OpenMP, you parallelize more and more loops, you add in more of these guys, and do you ever get back up to where you started? So as I've said, you don't know if you're going to recover the performance. You lose performance because you have to run fewer processes than CPU cores, but you gain it. What's nice about the shared memory MPI model is it's more plug or play. You can decide at any one time, do I implement this function using MPI processes behaving like threads, or do I leave it as the original MPI version? So you don't have to sort of So other use cases, saving memory. Some programs with large static lookup tables. In MPI, you need one copy per process. You can have one copy per node. This is a very technical thing. I put this in because I felt pleased with myself because I had a subroutine which did this, but this is a very corner case. I don't want to cover that. This is the real use case here. Okay, one lookup table per node, not per process. So with standard RMA, what you do is you publish local. So you have a model which allows you to, through function calls, directly read and write to shared arrays with these windows. However, that has a big overhead because you've got a function call, a very complicated function call to potentially read or write one integer. So people said, well, sometimes if those two processes, if the origin and the target are on the same node, it seems crazy. I want to access memory on the same node in shared memory, and I have to do a function call. It's crazy, okay? So with standard RMA, you publish the local memory in the collective shared window. You do read and write with puts and gets, and you do appropriate synchronization. This is wasteful. I know why can't all processes just read and write directly to this window after you do an OpenMP? So the requirement is technically it requires the unified model. As I said, that means that the windows aren't implemented through intermediate copies of data, but that is always true. As I said, this is not a restriction in practice for standard CPU architectures. So the procedure, first of all, for the first time in MPI, we're going to have to know which processes share the node. It's only possible for two MPI processes to directly read and write to each other's memory if they are physically on the same node, the same shared memory computer. So what you have to do is all your processes that live on the same node have to join their own communicator. So you have one communicator for each node. There is support in MPI to do that. Then for all the processes on a node, there's a shared allocation routine where you collectively allocate a shared array. Each process receives a local array, but the model is the operating system can arrange for the local array to be part of a single global array. So imagine you only had two processes on a node, rank 0 and rank 1. Rank 0 might allocate 10 integers, rank 1 might allocate another 10 integers. But if it's a shared array, the operating system makes sure that those two blocks of 10 are actually together in a single block of 20. So that requires some operating system magic. But although each process may allocate memory individually, globally, it's all part of a single shared array. And that means that you can access, so if you have a local array, if you do local array 0, that's the first element of your slice. It looks really nasty. If you do local array of -1, it's now the last element of the previous guy. I'll do a diagram later on. It looks really nasty, but you can do halo swapping by simply over-indexing and under-indexing your local arrays, because the operating system has made sure that that memory exists. You need appropriate synchronization for remote accesses. You still need MPI calls for inter-node communication. So, this doesn't solve your node-to-node stuff, but it's good on a node. So first of all, how do we create subcommunicators which are all processes on a node live in the same communicator? Well, there's a routine called MPI split type. So you pass in MPI world, and it will split it down into subcommunicators, these new communicators, based on some split type. Now, originally there was only one. This is a completely general routine. There was only one split type called MPI type shared. But the idea is this is an extensible routine, and they have extended it now. Well, for example, on a heterogeneous system, you might want to say, this might be MPI, the split type might be MPI type accelerator. You might say, I want all the processes which live on nodes which have accelerators to be a subcommunicator. So that's why they made it into a general routine, but we'll just use it with split type MPI type shared. So all the processes that live on the same node get grouped together into the same subcommunicator. How are they ordered within that node? Well, you can give a key, a key specified the local ordering. But if you just specify the key as being your ranking world, then the ordering is the same. So this isn't particularly important. Whoops. And there is an info which I will not. Sorry, something has gone wrong with my screen. There is an info which, again, you'd have to look up the manual pages. This is extra information. It's not particularly critical. So this allows you to give a world and split it with split type as MPI type shared, and specify MPI info null, and everyone who's in the same node will be part of the same subcommunicator, which is nice. So that allows us then to have groups of processes grouped by node. So if I had is world size 12, and I've got 2 nodes, each with 6 processes. In world, they're numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, split across the 2 nodes. If I call MPI split type of world type shared rank info null and node within node okay, these guys get to put into one node which has size equals 6, and their ranks are the same as the original ones, 0 to 5. These guys get put into another node the size is 6, but their ranks within node are now 0 to 5. Remember, your rank is local to your communicator. So because node is of size 6, your local rank is of 0 to 5. So you have 2 identities, your global rank and your local rank within the communicator. And that's something you have to remember. So having done that, we now need to allocate the array. It's a slightly different routine. If you remember, in the normal RMA model, processes allocate data, and it's a bottom-up model. They are then put together into a global window. We saw here that the arrays are going to be magically allocated so that even though they're on different processes, they line up in memory. So clearly you can't do that. So MPI when allocate shared doesn't just create the window, it allocates the data. So in the previous model, you supplied data, you supplied the allocated data to construct the window. Here you just say, give me the window and give me the data. So MPI when allocate shared. So give me a node local shared window, which is of this size, this displacement unit, just like in the normal window creation, and you pass a base pointer. This gives you back the pointer to the local array, and this gives you back the window. Okay, so this does the allocate. This is like a malloc into base pointer, and this is where Fortran, you have to do jiggery pokery in Fortran to convert this into a Fortran array. It's in the example if you want to look. But basically, this is like MPI win create, except it doesn't just create the window, it also allocates the data. That's the Fortran. Size window size bytes distributed the counting unit. The info MPI info null. Is the parent. It must be within a single node. If not, it will complain. You cannot allocate a shared window across different nodes. The base pointer is the allocated storage, and the allocated window is the window. So if you want to do puts and gets, you need to use the window. If you want to direct read and write, you can directly read and write to this base pointer. It's just like a normal array. So for the traffic model example, what we would do is let's assume we've got a node com, we've got the old road, we've got a node window, and we've got a couple of extra things here. The win size then local plus 2 times size of int as before. The displacement is the size of int. But what we do is MPI win allocate shared win size, which is this many bytes, including the halos. Disp unit is integers. Node com is, assuming I pre-created that. Old road gives me back the pointer. That's where the allocated storage goes. And node win is it sets up the window. And for this shared memory access, we actually will just directly read and write to the old road array rather than accessing it via the window through puts and get. You have the choice. But so the important point is, if we have n local equals 2, the arrays of size 4, and on node rank 0, we have x0, x1, x2, x3. On node rank we have it. So locally, because win size is 4 integers, every process allocates 4 integers. But globally, they're part of a bigger row of size 12. Because by default, it's a contiguous block of memory across processes. You can relax that, but that's what you want. So basically, if I want to access the extreme value of x0, node rank can just call that x minus 1. Or if I wanted to access the end of node rank 2s, I could call that x7, or this one is x4. So that might seem nasty to you. You've got an array of size 3 and you're over-indexing it, but it's C, it's pointers, so you'll never complain. So in Fortran, you might have to be careful about not doing bounds checking. But so that really is the model. And basically, you have a special shared allocation routine, and once you've done that, you have this shared array, and you can just read and write to it as you want. You might, so in the previous diagram, rank 1 can access rank 0's x0 by referencing to it as its own x minus 4. Okay, so basically rank 1 can access that value there by calling x minus 1, minus 2, minus 3, minus 4. If this was a shared lookup table, it'd be nice if node rank 1 just had a pointer which started here. Okay, you might think that you could just say, well, can node rank 0 not just MPI send me its pointer for the base array here? That doesn't work for technical reasons. So there's a strange routine called MPI win shared query. I can go into this a bit later. It's slightly weird, but it gives us the local pointer which we can use to access remote data. Okay. If I want to know what the address of the array is on node rank 0, that address there, I cannot just get, due to the way that virtual memory works, I have to call a special routine, MPI win shared query, which says give me a pointer which is equivalent to that one on rank 0. It's a slight it's a slight technicality, but it is important, and it's illustrated in that Stack Overflow example that I posted. But for here, we're not interested in that. Here, we only want to access our neighbors' data in the traffic model, and that's easiest done with this over and under indexing of arrays. Synchronization, we can now do halo swap by direct copies, but again, just like to synchronize, you need to use win fence. So basically, it's very similar to OpenMP. In OpenMP, you bracket remote memory access with barriers or parallel regions. What we do here is we just do it. So what we say is we're about to do some local reads and writes. We need to synchronize MPI win fence node win. We then do we don't do send and receive. We just write my what are we doing here? So I wrote this code, but I should. Okay, fine. We are basically yes, exactly. We are writing. This doesn't look right. Old road of n local plus 1. Old road of. Oh yes, it is correct. Sorry. On n local plus 1 is old road n local minus 1. I think that is actually. That's okay. I forgot that n local. That I've made this. This is wrong. Sorry, because I haven't taken into account the halos. So it should actually be. Apologies for this. This is clearly something I've not. It's very. What I'm doing is I'm trying to write the halos. I'm trying to write that data value into there and that data value into there. Okay, but that is not the correct. So you would right. So that's a very good question. I will cover that when I show you the solution. So that's a very good question. You have to be careful there. So so this is the general case. So this is correct. This is actually on local of n local. I think that's what it should be. Yes. Okay. That's what it should be. I will save that. And apologies, that was a slight mistake. Very good question from David. Yep. So this is only true for the interior processes. On the end processes, which is these guys here, you'll have to do a send and a receive. That's very good. So this is a generic statement, but you're actually right. It doesn't work on the extreme processes. And so direct read and write when it works. Yes. Oh, there we go. Yeah. Still the MPIs for internode. If you node rank will do node rank to do, so that's what we call MPI send receive. So yeah, it's natural that in this example, this example here, that this guy node rank 0 would send off that data and node rank. In fact, any rank can access any data. So you could have all the MPI communicators done by node rank 0 for the whole array, but that's slightly perverse. And of course, the internode sends and receives have to take place in MPI com world. You're not sending within MPI com node because that's local. So there's a bit of playing around here. And if I show you so the conclusion, so it's a relatively simple syntax for shared memory and MPI, much better than roll your own solutions. The roll your own solutions would involve using lower level calls like Unix shared memory segments, and I would advise you not to do that. The possible use cases are on-node communication without needing MPI, which could be more efficient if we think about ECMWF, the wind example, or one copy of static data per node, not per process. I think the advantage of an incremental plug and play approach, it doesn't mean that you have to. You can choose to leave a function in pure MPI or in this RMA one, which you can't do in MPI+OpenMP. Once you've got MPI+OpenMP, every function has to have OpenMP in it, otherwise it will run slowly. The disadvantages are there's no OMP schedule. You have to do a lot of stuff yourself, and this is a slightly technical point, but yeah, you may not get rid of the halos entirely. Again, I don't want to dwell on this point, but there is other than the simple case of one static copy of static data per node, I could go into the details, but it's not clear that this saves you memory if you have halos. It means you have to completely replace all the halos by RMA. So in that sense, it's not plug and play. But that's a bit of a whiz through how it works. But if I basically show you, and this hopefully will answer David's question, if I go to this guy here, if I look at the traffic SM, which is the shared memory, it all looks very similar as before. But now I have my node com and lots of node sizes and things like that, node win and bits and pieces. This is all the same. Here we create the node local communicator, MPI com split type, split com world, based on into subgroups which share memory, keep the same rank in the old communicator as the new one, same ordering. Basically, to check it all when it's expected, basically there's a routine called MPI get processor name, which is actually get node name. I like that because you can say, you know, rank percent the incom world is ranked. This is just a debugging thing, but I like to do this. Rank percent is rank percent node com on node blah, and you know the name. That's quite fun to do. I no longer malloc overrode. No, this is fine, David. What's your question? No, there is this. Okay, what's your question? I'm interested. What is it? You can ask it in chat if you want, or you can do it on in the mic. It's up to you. Right. So so this comes back to my yes. So you're absolutely right. I was assuming here, this was my statement about, I was assuming here that other parts of the program, so I was assuming here at the very top level, the roads are allocated with halos because some parts of the algorithm and the real code might still do that, but you're optimizing this particular routine. So there are three levels of sophistication. One is MPI everywhere. The other is MPI in some places still leave the halos, but do explicit halo swapping with copies. But you're right. The ultimate would be to say, look, I wouldn't have any halos on these, or other than the very extreme ones, and I don't need to do halo swap. But I think it's a slight. But the problem. My thought was, this allows you to do a plug and play, a routine which updates the road using point-to-point MPI or a combination MPI and shared memory without changing the way that the arrays are allocated, which might affect but you're right, in a real program that would have global implication for the program. Do you see what I mean? You'd have to change it everywhere. You're right, there's no need to do halo swapping within the node, except that my assumption was that the user still wanted, for other reasons, to have halos on the data. Does that explain does that kind of answer where I was coming from? It is a very good question, though. Yeah. And that was my statement as to why this doesn't necessarily reduce your memory usage, because there's still halos there. It's annoying. It's ugly. There's this junk. It would be much nicer if it was a pure array. And in fact, I think I would probably do that in reality here. I would do that. But you would have to go and make sure that all the other parts of the program are consistent with that. So old road is no longer mallocked. It is created by this routine. So it's the same as before, but MPI when allocate shared previously just gave me the node win. Now it gives me the old road. And then basically I can from then on do exactly what I did before. It's all the same stuff as before. So this is exactly what David was pointing out. This direct, yeah, so that was the old road of then local plus 2. That this, yeah, is saying if I'm not the extreme rightmost one, do that. If I'm not the extreme leftmost one, do that. And then we do standard MPI communications at the endpoints, which we can do like that. So does that answer your question, David? Or was it David? Sorry, I scrolled off. Yes. So yes, does that you'll see that I have these in a real program. I have these protected by only these guys do this, and then here. But you're right. If we didn't have internal halos, we wouldn't need this at all. We could just go and call the MPI. We could just go and call the update road, and there we go. So the magic is the what you call it magic or weirdness is this stuff here, that you can write to your neighbor's array by over-indexing your local array, and similarly write down the way by under-indexing your local array. I think there is there a comment here? Now, I've made an implicit assumption here that which I really ought to check in a real code. But the implicit assumption is that, if I go back to my slides, the implicit assumption is that right from the start, the ranks were laid out like this, that they were, so that the lowest and highest ranks on a node are, well, actually that the ranks are consecutive within a node. So this code implicitly assumes this, that the ranks are allocated linearly across nodes. That is normally true, but isn't guaranteed. So you really ought to test in your code. You know, once you've done the node com, you should really check that all the ranks that are in node com are the ones you expect, that they're consecutive. That's so I am denied about that, but that is an implicit assumption here you have to be careful about. But hopefully the model is clear, and if I go to the where is the, so I answered the question many years ago on Stack Overflow, where someone asked a similar question. It's no. Oh, sorry. I've got 2 new windows here. I will, yeah. I'm getting very, yes. So this is the Stack Overflow post. Yeah, there we go. So what I did here is the example which David asked about, where I said, here's a table that sets up a small, here's a code that sets up a small table in each shared memory node. Only one process actually allocates an index table, all the processes can read it. So what I do here, there's lots of, I was a bit pedantic in this example, but I declare rank 0 declares a table of size 5. Sorry, on each node there's a table of size with 5 entries in it, and I do that by when I do MPI when allocate shared. The local table size is 0 unless your node rank is 0. So basically, when we do this shared when allocate shared, everybody allocates 0 space except for the node rank 0. That's the lowest rank on each node, who allocates 5. And then there was a lot of pedantic checking here. Is basically node rank 0 initializes all the data for the table. So only rank 0 initializes the table, and then afterwards every rank can get that value. And the weird thing is here, this MPI win shared query is saying, give me a pointer which points to the 0th entry. Sorry, which points to the which is the same as the pointer on rank 0, on node rank 0. This is a slightly strange thing. Take back table. Where's WinDisp? That's why I don't understand. I can't understand my own code. This was like, okay. I can't remember the syntax of MPI win shared query, which is a bit embarrassing. But this illustrates that use case which someone asked about. I should basically you see that? When shared query. Query the size and base pointer. Okay, fine. I'm saying okay. So what I'm saying is, give me the pointer to the data on rank 0, but it also tells me how big it is. Sorry, that was the thing. That's what I got confused about. Is it less efficient since all ranks are? Yes. So you have a choice. So this is my statement about NUMA allocation. For a table size of 5, it's really a moot point. But if you had a large one, yes, it would probably to get the NUMA allocation correct, it would be better. Well, yes, potentially less efficient. That's right. You're right. It's simpler and maybe more natural to have only rank 0 allocated, but potentially less efficient in terms of memory access. So yes, in a real case for a very large lookup table, you might be better to have every rank supply a portion of it, and therefore the data will be located. I don't know. I don't know. Maybe. It's a good question. It's a 50-50. I can think of for big tables, it's probably better to spread it across the ranks. Yes, it will work in both cases, but for big tables, you probably want to spread it across the ranks. You're probably right. Yeah. The problem with spreading it across the ranks is you then have to worry about what happens if the table size doesn't fit into the number of ranks. So you have to do remainders and stuff. It gets a bit messy. You can do it, but it's just a bit messier. Does that make sense? But yes, you're right. I think for a big array, I would allocate it across them to at least have even memory layout. That might make you feel a bit more what's the word? The thing I didn't go into before is if you allocate an enormous table only on rank 0, that can blow all the memory in that NUMA region. So all memory allocations for rank 0, even in MPI, are in the wrong NUMA region. It's an extreme case, but I have seen that happen. So yes, if you're being defensive, you would do what you suggest and have every process supply a subset of the memory, not rank 0 supply at all. And it would be make me feel a bit more happy for large data arrays. Yeah, but you have to worry about remainders then and such like. So I mean, I've given you the solutions here because it's way too much to expect you to write the stuff in the time. But I mean, the way the timetable works, it was a practical till 3:30, then a tea break, and then I'll be back at 4 to answer questions. I don't know if anyone has any questions now, but I think you have all the material there. You have in traffic. We have all the implementations in traffic RMA. No, I think it's just called RMA. We have the CMP RMA. I will just, for the Fortran programs, I will just show you the trick. It's horrible. So the problem you have in Fortran, this all looks exactly the same, except MPI when allocate shared, yeah, gives me back a base pointer, but that is a C pointer. It's a, oh, sorry, am I sharing the right thing? Yes, that's a C pointer. Now in modern Fortran, arrays aren't pointers, they are they're array descriptors. So we have to take this base pointer and create a Fortran array from it, and that is a function that's available in one of these nasty, where is it? ISO, one of these modules. You have to declare it as a type C pointer. It's all horrible. Mainly because C is horrible. It's horrible because C is horrible, not because Fortran is horrible. And then you have to say call CF pointer. So this coerces the base pointer into an array of this shape. The problem is, in my Fortran codes, I use the trick of changing the indices not to start from 1 to start from 0. So I then have to do this horrible thing of aliasing the old road to do. This is a stupid routine. This CF pointer should allow you not just specify the shape of the array, but also the starting indices. But it doesn't. It's stupid. I actually sent an email to the Fortran standards people about this, but they ignored me because I thought it was stupid. But this is just the fact that Fortran arrays are proper arrays. You can ask them how big they are, but that means that this allocation routine here, giving you back a bare pointer, isn't any good, and you have to do a bit of jiggery pokery to get it into the right format. But you can do it. You can do it. It's not a big deal. It's just annoying. So like I said, that was the last thing. I'm around now for it's been quite a tough couple of days. I think well, dense couple of days. I get you. I'm sure you have other things. You're welcome to stay around. I said I'll be around till put up a. I'll be around until 3:30, and then back at 4. I'm happy to answer questions then and have a chat about anything you might want to talk about. But that's all the material presented, and I'll stop the recording.